Section 11, Chapter 10 of Creative Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, 2010. Creative Chemistry by Edwin E. Slosson. Chapter 10. What Comes from Corn? The discovery of America dowered mankind with a world of new flora. The early explorers, in their haste to gather up gold, paid little attention to the more valuable products of field and forest, but in the course of centuries their usefulness has become universally recognized. The potato and tomato, which Europe at first considered as unfit for food, or even as poisonous, have now become indispensable among all classes. New World drugs like quinine and cocaine have been adopted into every pharmacopoeia. Cocoa is proving a rival of tea and coffee, and even the banana has made its appearance in European markets. Tobacco and chicle occupy the nostrils and jaws of a large part of the human race. Maize and rubber are become the common property of mankind, but still may be called American. The United States alone raises 4/5 of the corn and uses 3/4 of the caoutchouc of the world. All flesh is grass. This may be taken in a dietary as well as a metaphorical sense. The gramineaceae provide the greater part of the sustenance of man and beast. Hay and cereals, wheat, oats, rye, barley, rice, sugarcane, sorghum, and corn. From an American viewpoint, the greatest of these, physically and financially, is corn. The corn crop of the United States for 1917, amounting to 3,159,000,000 bushels, brought in more money than the wheat, cotton, potato, and rye crops all together. When Columbus reached the West Indies he found the savages playing with rubber balls, smoking incense sticks of tobacco, and eating cakes made of a new grain that they called maíz. When Pizarro invaded Peru, he found this same cereal used by the natives not only for food, but also for making alcoholic liquor, in spite of the efforts of the Incas to enforce prohibition. When the Pilgrim Fathers penetrated into the woods back of Plymouth Harbor, they discovered a cache of Indian corn. So throughout the three Americas, from Canada to Peru, corn was king, and it has proved worthy to rank with the rival cereals of other continents, the wheat of Europe and the rice of Asia. But food habits are hard to change, and for the most part the people of the Old World are still ignorant of the delights of hasty pudding and Indian pudding, of hoe cake and hominy, of sweet corn and popcorn. I remember 30 years ago seeing on a London stand a heap of dejected popcorn balls labeled "Novel American Confection. Please try one." But nobody complied with this pitiful appeal but me, and I was sorry that I did. Americans used to respond with a shipload of corn whenever an appeal came from famine sufferers in Armenia, Russia, Ireland, India, or Austria, but their generosity was chilled when they found that their gift was resented as an insult or as an attempt to poison the impoverished population, who declared that they would rather die than eat it, and some of them did. Our Department of Agriculture sent maize missionaries to Europe with farmers and millers as educators and expert cooks to serve free flapjacks and pones, but the propaganda made little impression, and today Americans are urged to eat more of their own corn because the famished families of the war-stricken region will not touch it. Just so the beggars of Munich revolted at potato soup when the pioneer of American food chemists, Bumford, attempted to introduce this transatlantic dish. But here we are not so much concerned with corn foods as we are with its manufactured products. If you split a kernel in two, you will find that it consists of three parts: a hard and horny hull on the outside, a small oily and nitrogenous germ at the point, and a white body consisting mostly of starch. Each of these is worked up into various products, as may be seen from the accompanying table. The hull forms bran and may be mixed with the gluten as a cattle food. The corn steeped for several days with sulfurous acid is disintegrated and on being ground the germs are floated off, the gluten or nitrogenous portion washed out, the starch grains settled down, and the residue pressed together as oil cake fodder. The refined oil from the germ is marketed as a table or cooking oil under the name of mazola, and comes into competition with olive, peanut, and cottonseed oil in the making of vegetable substitutes for lard and butter. Inferior grades may be used for soaps, or for glycerin and perhaps nitroglycerin. A bushel of corn yields a pound or more of oil. From the corn germ also is extracted a gum called paragol that forms an acceptable substitute for rubber in certain uses. The red rubber sponges and the eraser tips to pencils may be made of it and can contribute some 20% to the synthetic soles of shoes. Starch, which constitutes 55% of the corn kernel, can be converted into a variety of products for dietary and industrial uses. As found in corn, potatoes, or any other vegetables, starch consists of small, round, white, hard grains, tasteless and insoluble in cold water. But hot water converts it into a soluble, sticky form which may serve for starching clothes or making cornstarch pudding. Carrying the process further with the aid of a little acid or other catalyst, it takes up water and goes over into a sugar, dextrose, commonly called glucose. Expressed in chemical shorthand, this reaction is C6H10O5 starch plus H2O water goes to C6H12O6 dextrose. This reaction is carried out on 40 million bushels of corn a year in the United States. The starch milk, that is, the starch grains washed out from the disintegrated corn kernel by water, is digested in large pressure tanks under 50 pounds of steam with a few tenths of 1% of hydrochloric acid until the required degree of conversion is reached. Then the remaining acid is neutralized by caustic soda and thereby converted into common salt, which in this small amount does not interfere but rather enhances the taste. The product is the commercial glucose or corn syrup, which may, if desired, be evaporated to a white powder. It is a mixture of three derivatives of starch in about this proportion: maltose 45%, dextrose 20%, dextrin 35%. There are also present 3 or 4/10 of 1% salt and as much of the corn protein and a variable amount of water. It will be noticed that the glucose, dextrose, which gives name to the whole, is the least of the three ingredients. Maltose, or malt sugar, has the same composition as cane sugar, C12H22O11, but is not nearly so sweet. Dextrin, or starch paste, is not sweet at all. Dextrose or glucose is otherwise known as grape sugar, for it is commonly found in grapes and other ripe fruits. It forms half of honey and is one of the two products into which cane sugar splits up when we take it into the mouth. It is not so sweet as cane sugar and cannot be so readily crystallized, which, however, is not altogether a disadvantage. The process of changing starch into dextrose that takes place in the great steam kettles of the glucose factory is essentially the same as that which takes place in the ripening of fruit and in the digestion of starch. A large part of our nutriment, therefore, consists of glucose either eaten as such in ripe fruits or produced in the mouth or stomach by the decomposition of the starch of unripe fruit, vegetables, and cereals. Glucose may be regarded as a predigested food. In spite of this well-known fact, we sometimes read poor food articles in which glucose is denounced as a dangerous adulterant and even classed as a poison. The other ingredients of commercial glucose, the maltose and dextrin, have of course the same food value as the dextrose, since they are made over into dextrose in the process of digestion. Whether the glucose syrup is fit to eat depends, like anything else, on how it is made. If, as was formerly sometimes the case, sulfuric acid was used to effect the conversion of the starch, or sulfurous acid to bleach the glucose, and these acids were not altogether eliminated, the product might be unwholesome or worse. Some years ago in England there was a mysterious epidemic of arsenical poisoning among beer drinkers. On tracing it back it was found that the beer had been made from glucose, which had been made from sulfuric acid, which had been made from sulfur, which had been made from a batch of iron pyrites which contained a little arsenic. The replacement of sulfuric acid by hydrochloric has done away with that danger, and the glucose now produced is pure. The old recipe for homemade candy called for the addition of a little vinegar to the sugar syrup to prevent graining. The purpose of the acid was of course to invert part of the cane sugar to glucose, so as to keep it from crystallizing out again. The professional candy maker now uses the corn glucose for that purpose, so if we accuse him of adulteration on that ground we must levy the same accusation against our grandmothers. The introduction of glucose into candy manufacture has not injured but greatly increased the sale of sugar for the same purpose. This is not an uncommon effect of scientific progress, for as we have observed, the introduction of synthetic perfumes has stimulated the production of odoriferous flowers and the price of butter has gone up with the introduction of margarine. So, too, there are more weavers employed and they get higher wages than in the days when they smashed up the first weaving machines, and the same is true of printers and typesetting machines. The popular animosity displayed toward any new achievement of applied science is never justified, for it benefits not only the world as a whole, but usually even those interests with which it seems at first to conflict. The chemist is an economizer. It is his special business to hunt up waste products and make them useful. He was, for instance, worried over the waste of the cores and skins and scraps that were being thrown away when apples were put up. Apple pulp contains pectin, which is what makes jelly gel, and berries and fruits that are short of it will refuse to gel. But using these for their flavor, he adds apple pulp for pectin and glucose for smoothness and sugar for sweetness and, if necessary, synthetic dyes for color. He is able to put on the market a variety of jellies, jams, and marmalades at very low price. The same principle applies here as in the case of all compounded food products. If they are made in cleanly fashion, contain no harmful ingredients, and are truthfully labeled, there is no reason for objecting to them. But if the manufacturer goes so far as to put strawberry seeds or hayseed into his artificial strawberry jam, I think that might properly be called adulteration, for it is imitating the imperfections of nature, and man ought to be too proud to do that. The old-fashioned open kettle molasses consisted mostly of glucose and other invert sugars together with such cane sugar as could not be crystallized out. But when the vacuum pan was introduced, the molasses was impoverished of its sweetness, and beet sugar does not yield any molasses. So we now have in its place the corn syrups consisting of about 85% of glucose and 15% of sugar, flavored with maple or vanillin or whatever we like. It is encouraging to see the billboards proclaiming the virtues of Karo syrup and Mazola oil, when only a few years ago the products of our national cereal were without honor in their own country. Many other products besides foods are made from corn starch. Dextrin serves in place of the old gum arabic for the mucilage of our envelopes and stamps. Another form of dextrin, sold as Cordex, is used to hold together the sand of the cores of castings. After the casting has been made, the scorched core can be shaken out. Glucose is used in place of sugar as a filler for cheap soaps and for leather. Altogether, more than 100 different commercial products are now made from corn, not counting cob pipes. Every year the factories of the United States work up over 50 million bushels of corn into 800 million pounds of corn syrup, 600 million pounds of starch, 230 million pounds of corn sugar, 625 million pounds of gluten feed, 90 million pounds of oil, and 90 million pounds of oil cake. 2 million bushels of cobs are wasted every year in the United States. Can't something be made out of them? This is the question that is agitating the chemists of the Carbohydrate Laboratory of the Department of Agriculture at Washington. They have found it possible to work up the corn cobs into glucose and xylose by heating with acid. But glucose can be more cheaply obtained from other starchy or woody materials, and they cannot find a market for the xylose. This is a sort of sugar, but only about half as sweet as that from cane. Who can invent a use for it? More promising is the discovery by this laboratory that by digesting the cobs with hot water there can be extracted about 30% of a gum suitable for bill posting and labeling. Since the starches and sugars belong to the same class of compounds as the celluloses, they also can be acted upon by nitric acid with the production of explosives like guncotton. Nitro sugar has not come into common use, but nitrostarch is found to be one of the safest of the high explosives. On account of the danger of decomposition and spontaneous explosion from the presence of foreign substances, the materials in explosives must be of the purest possible. It was formerly thought that tapioca must be imported from Java for making nitrostarch, but during the war, when shipping was short, the War Department found it could be made better and cheaper from our homegrown corn starch. When the war closed, the United States was making 1.72 million pounds of nitrostarch a month for loading hand grenades. So too, the Post Office Department discovered that it could use mucilage made of corn dextrin, as well as that which used to be made from tapioca. This is progress in the right direction. It would be well to divert some of the energetic efforts now devoted to the increase of commerce to the discovery of ways of reducing the need for commerce by the development of home products. There is no merit in simply hauling things around the world. In the last chapter we saw how dextrose or glucose could be converted by fermentation into alcohol. Since cornstarch, as we have seen, can be converted into dextrose, it can serve as a source of alcohol. This was, in fact, one of the earliest misuses to which corn was put, and before the war put a stop to it, 34 million bushels went into the making of whiskey in the United States every year, not counting the moonshiners' output. But even though we left off drinking whiskey, the distillers could still thrive. Mars is more thirsty than Bacchus. The output of whiskey, denatured for industrial purposes, is more than 3 times what it was before the war, and the price has risen from 30 cents a gallon to 67 cents. This may make it profitable to utilize sugars, starches, and cellulose that formerly were out of the question. According to the calculations of the Forest Products Laboratory of Madison, it costs from 37 to 44 cents a gallon to make alcohol from corn, but it may be made from sawdust at a cost from 14 to 20 cents. This is not wood alcohol, that is methyl alcohol, CH4O, such as is made by the destructive distillation of wood, but genuine grain alcohol, ethyl alcohol, C2H6O, such as is made by the fermentation of glucose or other sugar. The first step in the process is to digest the sawdust or chips with dilute sulfuric acid under heat and pressure. This converts the cellulose, wood fiber, in large part into glucose, corn sugar, which may be extracted by hot water in a diffusion battery as in extracting the sugar from beet chips. This glucose solution may then be fermented by yeast and the resulting alcohol distilled off. The process is perfectly practicable but has not yet been proved profitable. But the sulfite liquors of the paper mills are being worked up successfully into industrial alcohol. The rapidly approaching exhaustion of our oil fields, which the war has accelerated, leads us to look around to see what we can get to take the place of gasoline. One of the most promising of the suggested substitutes is alcohol. The United States is exceptionally rich in mineral oil, but some countries, for instance England, Germany, France, and Australia, have little or none. The Australian Advisory Council of Science, called to consider the problem, recommends alcohol for stationary engines and motor cars. Alcohol has the disadvantage of being less volatile than gasoline, so it is hard to start up the engine from the cold. But the lower volatility and ignition point of alcohol are an advantage in that it can be put under a pressure of 150 pounds to the square inch. A pound of gasoline contains 50% more potential energy than a pound of alcohol, but since the alcohol vapor can be put under twice the compression of the gasoline and requires only one-third the amount of air, the thermal efficiency of an alcohol engine may be 50% higher than that of a gasoline engine. Alcohol also has several other conveniences that can count in its favor. In the case of incomplete combustion, the cylinders are less likely to be clogged with carbon and the escaping gases do not have the offensive odor of the gasoline smoke. Alcohol does not ignite so easily as gasoline and the fire is more readily put out, for water thrown upon blazing alcohol dilutes it and puts out the flame, while gasoline floats on water and the fire is spread by it. It is possible to increase the inflammability of alcohol by mixing with it some hydrocarbon such as gasoline, benzene, or acetylene. In the Taylor-White process, the vapor from low-grade alcohol containing 18% water is passed over calcium carbide. This takes out the water and adds acetylene gas, making a suitable mixture for an internal combustion engine. Alcohol can be made from anything of a starchy, sugary, or woody nature, that is, from the main substance of all vegetation. If we start with wood, cellulose, we convert it first into sugar, glucose, and of course we could stop here and use it for food instead of carrying it on into alcohol. This provides one factor of our food, the carbohydrate, but by growing the yeast plants on glucose and feeding them with nitrates made from the air, we can get the protein and fat. So it is quite possible to live on sawdust, although it would be too expensive a diet for anybody but a millionaire, and he would not enjoy it. Glucose has been made from formaldehyde and this in turn made from carbon, hydrogen, and oxygen. So the synthetic production of food from the elements is not such an absurdity as it was thought when Berthelot suggested it half a century ago. The first step in the making of alcohol is to change the starch over into sugar. This transformation is effected in the natural course of sprouting by which the insoluble starch stored up in the seed is converted into the soluble glucose for the sap of the growing plant. This malting process is that mainly made use of in the production of alcohol from grain. But there are other ways of effecting the change. It may be done by heating with acid, as we have seen, or according to a method now being developed, the final conversion may be accomplished by mold instead of malt. In applying this method, known as the amylo process, to corn, the meal is mixed with twice its weight of water, acidified with hydrochloric acid and steamed. The mash is then cooled down somewhat, diluted with sterilized water, and inoculated with the mucor filaments. As the mash molds the starch is gradually changed over to glucose, and if this is the product desired, the process may be stopped at this point. But if alcohol is wanted, yeast is added to ferment the sugar. By keeping it alkaline and treating with the proper bacteria, a high yield of glycerin can be obtained. In the fermentation process for making alcoholic liquors, a little glycerin is produced as a byproduct. Glycerin, otherwise called glycerol, is an intermediate between sugar and alcohol. Its molecule contains 3 carbon atoms, while glucose has 6 and alcohol 2. It is possible to increase the yield of glycerin, if desired, by varying the form of fermentation. This was desired most earnestly in Germany during the war, for the British blockade shut off the importation of the fats and oils from which the Germans extracted the glycerin for their nitroglycerin. Under pressure of this necessity they worked out a process of getting glycerin in quantity from sugar, and, news of this being brought to this country by Dr. Alonzo Taylor, the United States Treasury Department set up a special laboratory to work out this problem. John R. Eoff and other chemists working in this laboratory succeeded in getting a yield of 20% of glycerin by fermenting blackstrap molasses or other syrup from California wine yeast. During the fermentation it is necessary to neutralize the acetic acid formed with sodium or calcium carbonate. It was estimated that glycerin could be made from waste sugars at about a quarter of its wartime cost, but it is doubtful whether the process would be profitable at normal prices. We can, if we like, dispense with either yeast or bacteria in the production of glycerin. Glucose syrup suspended in oil under steam pressure with finely divided nickel as a catalyst and treated with nascent hydrogen will take up the hydrogen and be converted into glycerin. But the yield is poor and the process expensive. Food serves substantially the same purpose in the body as fuel in the engine. It provides the energy for work. The carbohydrates, that is, the sugars, starches, and celluloses, can all be used as fuels and can all, even, as we have seen, the cellulose, be used as foods. The final products, water and carbon dioxide, are in both cases the same, and necessarily therefore the amount of energy produced is the same in the body as in the engine. Corn is a good example of the equivalence of the two sources of energy. There are few better foods and no better fuels. I can remember the good old days in Kansas when we had corn to burn. It was both an economy and a luxury, for, at 10 cents a bushel, it was cheaper than coal or wood, and preferable to either at any price. The long yellow ears, each wrapped in its own kindling, could be handled without crocking the fingers. Each kernel as it crackled sent out a blazing jet of oil, and the cobs left a fine bed of coals for the corn popper to be shaken over. Driftwood in the pyrotechnic fuel they make now by soaking sticks in strontium and copper salts cannot compare with the old-fashioned corn-fed fire in beauty and the power of evoking visions. Doubtless such luxury could be condemned as wicked nowadays, but those who have known the calorific value of corn would find it hard to abandon it altogether, and I fancy that the Western farmer's wife, when she has an extra batch of baking to do, will still steal a few ears from the crib. End of chapter 10. End of section 11. Section 12, Chapter 11, of Creative Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, 2010. Creative Chemistry by Edwin E. Slosson. Chapter 11. Solidified Sunshine. All life and all that life accomplishes depend upon the supply of solar energy stored in the form of food. The chief sources of this vital energy are the fats and the sugars. The former contain 2¼ times the potential energy of the latter. Both, when completely purified, consist of nothing but carbon, hydrogen, and oxygen, elements that are to be found freely everywhere in air and water. So when the sunny Southland exports fats and oils, starches and sugar, then it is sending away nothing material but what comes back to it in the next wind. What it is sending to the regions of more slanting sunshine is merely some of the surplus of the radiant energy it has received so abundantly, compacted for convenience into a portable and edible form. In previous chapters I have dealt with some of the uses of cotton, its employment for cloth, for paper, for artificial fibers, for explosives, and for plastics. But I have ignored the thing that cotton is attached to, and for which, in the economy of nature, the fibers are formed, that is, the seed. It is as though I had described the aeroplane and ignored the aviator whom it was designed to carry. But in this neglect I am but following the example of the human race, which for 3,000 years used the fiber but made no use of the seed except to plant the next crop. Just as mankind is now divided into the two great classes, the wheat eaters and the rice eaters, so the ancient world was divided into the wool wearers and the cotton wearers. The people of India wore cotton, the Europeans wore wool. When the Greeks under Alexander fought their way to the Far East, they were surprised to find wool growing on trees. Later travelers returning from Cathay told of the same marvel, and travelers who stayed at home and wrote about what they had not seen, like Sir John Maundeville, misunderstood these reports and elaborated a legend of a tree that bore live lambs as fruit. Here, for instance, is how a French poetical botanist, Delacroix, described it in 1791, as translated from his Latin verse. Upon a stalk is fixed a living brute. A rooted plant bears quadruped for fruit. It has a fleece, nor does it want for eyes, and from its brows 2 woolly horns arise. The rude and simple country people say it is an animal that sleeps by day, and wakes at night, though rooted to the ground, to feed on grass within its reach around. But modern commerce broke down the barrier between East and West. A new cotton country, the best in the world, was discovered in America. Cotton invaded England and after a hard fight, with fists as well as finance, wool was beaten in its chief stronghold. Cotton became king and the wool sack in the House of Lords lost its symbolic significance. Still 2/3 of the cotton crop, the seed, was wasted, and it is only within the last 50 years that methods of using it have been developed to any extent. The cotton crop of the United States for 1917 amounted to about 11 million bales of 500 pounds each. When the Great War broke out, and no cotton could be exported to Germany and little to England, the South was in despair, for cotton went down to 5 or 6 cents a pound. The national government, regardless of states' rights, was called upon for aid and everybody was besought to buy a bale. Those who responded to this patriotic appeal were well rewarded, for cotton rose as the war went on and sold at 29 cents a pound. But the chemist has added some $150 million a year to the value of the crop by discovering ways of utilizing the cottonseed that used to be thrown away or burned as fuel. The genealogical table of the progeny of the cottonseed herewith printed will give some idea of their variety. If you can examine a cottonseed, you will see first that there is a fine fuzz of cotton fiber sticking to it. These linters can be removed by machinery and used for any purpose where length of fiber is not essential. For instance, they may be nitrated as described in previous articles and used for making smokeless powder or celluloid. On cutting open the seed, you will observe that it consists of an oily, mealy kernel encased in a thin brown hull. The hulls, amounting to 700 or 900 pounds in a ton of seed, were formerly burned. Now, however, they bring from $4 to $10 a ton because they can be ground up into cattle feed or paper stock or used as fertilizer. The kernel of the cottonseed on being pressed yields a yellow oil and leaves a mealy cake. This last, mixed with the hulls, makes a good fodder for fattening cattle. Also, adding 25% of the refined cotton meal to our war bread made it more nutritious and no less palatable. Cottonseed meal contains about 40% of protein and is therefore a highly concentrated and very valuable feeding stuff. Before the war, we were exporting nearly 500,000 tons of cottonseed meal to Europe, chiefly to Germany and Denmark, where it is used for dairy cows. The British yeoman, his country's pride, has not yet been won over to the use of any such new-fangled fodder, and consequently the British manufacturer could not compete with his continental rivals in the seed-crushing business, for he could not dispose of his meal cake by-product as did they. Let us now turn to the most valuable of the cottonseed products, the oil. The seed contains about 20% of oil, most of which can be squeezed out of the hot seed hydraulic pressure. It comes out as a red liquid of a disagreeable odor. This is decolorized, deodorized, and otherwise purified in various ways. By treatment with alkalis or acids, by blowing air and steam through it, by shaking up with fuller's earth, by settling and filtering. The refined product is a yellow oil suitable for table use. Formerly, on account of the popular prejudice against any novel food products, it used to masquerade as olive oil. Now, however, it boldly competes with its ancient rival in the lands of the olive tree, and America ships some 700,000 barrels of cottonseed oil a year to the Mediterranean. The Turkish government tried to check the spread of cottonseed oil by calling it an adulterant and prohibiting its mixture with olive oil. The result was that the sale of Turkish olive oil fell off because people found its flavor too strong when undiluted. Italy imports cottonseed oil and exports her olive oil. Denmark imports cottonseed meal and margarine and exports her butter. Northern nations are accustomed to hard fats and do not take to oils for cooking or table use as do the southerners. Butter and lard are preferred to vegetable oil and ghee, but this does not rule out cottonseed. It can be combined with the hard fats of animal or vegetable origin in margarine, or it may itself be hardened by hydrogen. To understand this interesting reaction, which is profoundly affecting international relations, it'll be necessary to dip into the chemistry of the subject. Here are the symbols of the chief ingredients of the fats and oils. Please look at them. Linoleic acid, C18H32O2. Oleic acid, C18H34O2. Stearic acid, C18H36O2. Don't skip these because you have not studied chemistry. That's why I'm giving them to you. If you had studied chemistry, you would know them without my telling. Just examine them and you will discover the secret. you will see that all three are composed of the same elements, carbon, hydrogen, and oxygen. Notice next the number of atoms in each element as indicated by the little low figures on the right of each letter. You observe that all three contain the same number of atoms of carbon and oxygen, but differ in the amount of hydrogen. This trifling difference in composition makes a great difference in behavior. The less the hydrogen, the lower the melting point. Or to say the same thing in other words, fatty substances low in hydrogen are apt to be liquids, and those with a full complement of hydrogen atoms are apt to be solids at the ordinary temperature of the air. It is common to call the former oils and the latter fats, but that implies too great a dissimilarity, for the distinction depends on whether we are living in the tropics or the Arctic. It is better, therefore, to lump them all together and call them soft fats and hard fats, respectively. Fats of the third order, the stearic group, are called saturated because they have taken up all the hydrogen they can hold. Fats of the other two groups are called unsaturated. The first, which have the least hydrogen, are the most eager for more. If hydrogen is not handy they will take up other things, for instance oxygen. Linseed oil, which consists largely, as the name implies, of linoleic acid, will absorb oxygen on exposure to the air and become hard. That is why it is used in painting. Such oils are called drying oils, although the hardening process is not really drying since they contain no water, but is oxidation. The semi-drying oils, those that will harden somewhat on exposure to the air, include the oils of cottonseed, corn, sesame, soybean, and castor bean. Olive oil and peanut oil are non-drying and contain oleic compounds, olein. The hard fats, such as stearin, palmitin, and margarine, are mostly of animal origin, tallow and lard, though coconut and palm oil contain a large proportion of such saturated compounds. Though the chemist talks of the fatty acids, nobody else would call them so because they are not sour, but they do behave like the acids in forming salts with bases. The alkali salts of the fatty acids are known to us as soaps. In the natural fats they exist not as free acids, but as salts of an organic base, glycerin, as I explained in a previous chapter. The natural fats and oils consist of complex mixtures of the glycerin compounds of these acids, known as olein, stearin, etc., as well as various others of a similar sort. If you will set a bottle of salad oil in the icebox, you will see it separate into two parts. The white, crystalline solid that separates out is largely stearin. The part that remains liquid is largely olein. You might separate them by filtering it cold, and if then you tried to sell the two products, you would find that the hard fat would bring a higher price than the oil, either for food or soap. If you tried to keep them, you would find that the hard fat kept neutral and sweet longer than the other. You may remember that the perfumes, as well as their odorous opposites, were mostly unsaturated compounds. So we find that it is the free and unsaturated fatty acids that cause butter and oil to become rank and rancid. Obviously, then, we could make money if we turn soft, unsaturated fats like olein into hard, saturated fats like stearin. Referring to the symbols, we see that all that is needed to effect the change is to get the former to unite with hydrogen. This requires a little coaxing. The coaxer is called a catalyst. A catalyst, as I have previously explained, is a substance that by its mere presence causes the union of two other substances that might otherwise remain separate. For that reason the catalyst is referred to as a chemical parson. Finely divided metals have a strong catalytic action. Platinum sponge is excellent but too expensive. So in this case nickel is used. A nickel salt mixed with charcoal or pumice is reduced to the metallic state by heating in a current of hydrogen. Then it is dropped into the tank of oil and hydrogen gas is blown through. The hydrogen may be obtained by splitting water into its two components, hydrogen and oxygen, by means of the electrical current, or by passing steam over spongy iron which takes out the oxygen. The steam of hydrogen blown through the hot oil converts the linoleic acid to oleic and then the oleic into stearic. If you figured up the weights from the symbols given above, you would find that it takes about 1 pound of hydrogen to convert 100 pounds of olein to stearin, and the cost is only about 1 cent a pound. The nickel is unchanged and is easily separated. A trace of nickel may remain in the product, but as it is very much less than the amount dissolved when food is cooked in nickel-plated vessels, it cannot be regarded as harmful. Even more unsaturated fats may be hydrogenated. Fish oil has hitherto been almost unusable because of its powerful and persistent odor. This is chiefly due to a fatty acid which properly bears the uneuphonious name of clupanodonic acid and has the composition of C18H28O2. By comparing this with the symbol of the odorless stearic acid C18H36O2, you will see that all the rank fish oil lacks to make it respectable is 8 hydrogen atoms. A Japanese chemist, Sugimoto, had discovered how to add them and now the reformed fish oil under the names of talgol and candelite serves for lubricant and even enters higher circles as soap or food. This process of hardening fats by hydrogenation resulted from the experiments of a French chemist, Professor Sabatier of Toulouse, in the last years of the last century, but, as in many other cases, the Germans were the first to take it up and profit by it. Before the war, the copra or coconut oil from the British Asiatic colonies of India, Ceylon, and Malaya went to Germany at the rate of $15 million a year. The palm kernels grown in British West Africa were shipped, not to Liverpool, but to Hamburg, $19 million worth annually. Here the oil was pressed out and used for margarine, and the residual cake used for feeding cows produced butter, or for feeding hogs produced lard. Half of the copra raised in the British possessions was sent to Germany, and half the oil from it was resold to the British margarine, candle, and soap makers at a handsome profit. The British chemists were not blind to this, but they could do nothing. First, because the English politician was wedded to free trade. Second, because the English farmer would not use oil cake for his stock. France was in a similar situation. Marseille produced 15.5 million gallons of oil from peanuts grown largely in the French African colonies, but shipped the oil cake on to Hamburg. Meanwhile, the Germans, in pursuit of their policy of attaining economic independence, were striving to develop their own tropical territory. The subjects of King George, who because they had the misfortune to live in India were excluded from the British South African dominions or mistreated when they did come, were invited to come to German East Africa and set to raising peanuts in rivalry to French Senegal and British Coromandel. Before the war, Germany got half of the Egyptian cottonseed and half of the Philippine copra. That is one of the reasons why German warships tried to check Dewey at Manila in 1898 and German troops tried to conquer Egypt in 1915. But the tide of war set the other way and the German plantations of palm nuts and peanuts in Africa have come into British possession and now the British government is starting an educational campaign to teach their farmers to feed oil cake like the Germans and their people to eat peanuts like the Americans. The Germans, shut off from the tropical fat supply, were hard up for food and soap, for lubricants and for munitions. Every person was given a fat card that reduced his weekly allowance to the minimum. Millers were required to remove the germs from their cereals and deliver them to the War Department. Children were set to gathering horse chestnuts, elderberries, linden balls, grape seeds, cherry stones, and sunflower heads, for those contain from 6 to 20% of oil. Even the blue bottle fly, hitherto an idle creature for whom Beelzebub found mischief, was conscripted into the national service and set to laying eggs by the billion on fish refuse. Within a few days there is a crop of larvae which, to quote the Chemische Zentralblatt, yields 45 grams per kilogram of a yellow oil. This product, we should hope, is used for axle grease and nitroglycerin. Although properly purified, it would be as nutritious as any other, to one who has no imagination. Driven to such straits, Germany would have given a good deal for one of those tropical islands that we are so careless about. It might have been supposed that since the United States possessed the best land in the world for the production of cottonseed, coconuts, peanuts, and corn, that it would have led all other countries in the utilization of vegetable oils for food. That this country has not so used its advantage is due to the fact that the new products have not merely had to overcome popular conservatism, ignorance, and prejudice, hard things to fight in any case, but have been deliberately checked and hampered by the state and national governments in defense of vested interests. The farmer vote is a power that no politician likes to defy, and the dairy business in every state was thoroughly organized. In New York, the oleomargarine industry that in 1879 was turning out products valued at more than $5 million a year was completely crushed out by state legislation. The output of the United States, which in 1902 had risen to 126 million pounds, was cut down to 43 million pounds in 1909 by federal legislation. According to the disingenuous custom of American lawmakers, the Act of 1902 was passed through Congress as a revenue measure, although it meant a loss to the government of more than $3 million a year over what might be produced by a straight 2 cents a pound tax. A wholesale dealer in oleomargarine was made to pay a higher license than a wholesale liquor dealer. The federal law put a tax of 10 cents a pound on yellow oleomargarine and a quarter of a cent a pound on the uncolored, but people, doubtless from pure prejudice, prefer a yellow spread for their bread, so the economical housewife has to work over her oleomargarine with the annatto which is given to her when she buys a package or, if the law prohibits this, which she is permitted to steal from an open box on the grocer's counter. A plausible pretext for such legislation is afforded by the fact that the butter substitutes are so much like butter that they cannot easily be distinguished from it unless the use of annatto is permitted to butter and prohibited to its competitors. Fraudulent sales of substitutes of any kind ought to be prevented, but the recent pure food legislation in America has shown that it is possible to secure truthful labeling without resorting to such drastic measures. In Europe, the laws against substitution were very strict, but not devised to restrict the industry. Consequently, the margarine output of Germany doubled in the 5 years preceding the war, and the output of England tripled. In Denmark, the consumption of margarine rose from 8.8 pounds per capita in 1890 to 32.6 pounds in 1912. Yet the butter business, Denmark's pride, was not injured, and Germany and England imported more butter than ever before. Now that the price of butter in America has gone over the 75-cent mark, Congress may conclude that it no longer needs to be protected against competition. The compound lards or lard compounds, consisting usually of cottonseed oil and oleosterin, although the latter may now be replaced by hardened oil, met with the same popular prejudice and attempted legislative interference, but succeeded more easily in coming into common use under such names as Cotto Suet, Cream Crisp, Cuxit, Corno, Cottolene, and Crisco. Oleomargarine, now generally abbreviated to margarine, originated, like many other inventions, in military necessity. The French government in 1869 offered a prize for a butter substitute for the army that should be cheaper and better than butter in that it did not spoil so easily. The prize was won by a French chemist, Mége Mouret, who found that by chilling beef fat the solid stearin could be separated from an oil, oleo, which was the substantially same as that in milk and hence in butter. Neutral lard acts the same. This discovery of how to separate the hard and soft fats was followed by improved methods for purifying them and later by the process for converting the soft into the hard fats by hydrogenation. The net result was to put into the hands of the chemist the ability to draw his materials at will from any land and from the vegetable and animal kingdoms and to combine them as he will to make new fat foods for every use, hard for summer, soft for winter, solid for the northerners and liquid for the southerners, white, yellow, or any other color, and flavored to suit the taste. The Hindu can eat no fat from the sacred cow. The Mohammedan and the Jew can eat no fat from the abhorred pig. The vegetarian will touch neither. Other people will take both. No matter, all can be accommodated. All the fats and oils, although they consist of scores of different compounds, have practically the same food value when freed from the extraneous matter that gives them their characteristic flavors. They are all practically tasteless and colorless. The various vegetable and animal oils and fats have about the same digestibility, 89%, and are all ordinarily completely utilized in the body, supplying it with 2¼ times as much energy as any other food. It does not follow, however, that there is no difference in the products. The margarine men accuse butter of harboring tuberculosis germs from which their product, because it has been heated or is made from vegetable fats, is free. The butter men retort that margarine is lacking in vitamins, those mysterious substances which in minute amounts are necessary for life and especially for growth. Both the claim and the objection lose a large part of their force where the margarine, as is customarily the case, is mixed with butter or churned up with milk to give it the familiar flavor, but the difficulty can be easily overcome. The milk used for either butter or margarine should be free or freed from disease germs. If margarine is altogether substituted for butter, the necessary vitamins may be sufficiently provided by milk, eggs, and greens. Owing to these new processes, all the fatty substances of all lands have been brought into competition with each other. In such a contest, the vegetable is likely to beat the animal and the southern to win over the northern zones. In Europe before the war, the proportion of the various ingredients used to make butter substitutes was as follows. Average composition of European margarine. Animal hard fats 25%, vegetable hard fats 35%, copra 29%, palm kernel 6%, vegetable soft fats 26%, cottonseed 13%, peanut 6%, sesame 6%, soybean 1%, water, milk, and salt 14%. This is not the composition of any particular brand, but the average of them all. The use of a certain amount of the oil of the sesame seed is required by the laws of Germany and Denmark because it can be easily detected by a chemical color test and so serves to prevent the margarine containing it from being sold as butter. Open sesame is the password to these markets. Remembering that margarine originally was made up entirely of animal fats, soft and hard, we can see from the above figures how rapidly they are being displaced by the vegetable fats. The cottonseed and peanut oils have replaced the original oleo oil, and the tropical oils from the coconut, copra, and African palm are crowding out the animal hard fats. Since now we can harden at will any of the vegetable oils, it is possible to get along altogether without animal fats. Such vegetable margarines were originally prepared for sale in India, but proved unexpectedly popular in Europe and are now being introduced into America. They are sold under various trade names suggesting their origin, such as Palmyra, Palmona, Milkonut, Cocos, coconut oleomargarine, and Nucoa nut margarine. The last named is stated to be made of coconut oil for the hard fat and peanut oil for the soft fat churned up with a culture of pasteurized milk to impart the butter flavor. The law requires such a product to be branded oleomargarine, although it is not. Such cases of compulsory mislabeling are not rare. You remember the pigs is pigs story. Peanut butter has won its way into the American menu without any camouflage whatever, and as a salad oil it is almost equally frank about its lowly origin. This nut, which grows on a vine instead of a tree and is dug from the ground like potatoes instead of being picked with a pole, goes by various names according to locality: peanuts, ground nuts, monkey nuts, arachides, and goobers. As it takes the place of cotton oil in some of its products, so it takes its place in the fields and oil mills of Texas left vacant by the boll weevil. The once despised peanut added some $56 million to the wealth of the South in 1916. The peanut is rich in the richest of foods, some 50% of oil and 30% of protein. The latter can be worked up into meat substitutes that will make the vegetarian cease to envy his omnivorous neighbor. Thanks largely to the chemist who has opened these new fields of usefulness, the peanut raiser got $1.25 a bushel in 1917 instead of the 30 cents that he got 4 years before. It would be impossible to enumerate all the above sources of vegetable oils, for all seeds and nuts contain more or less fatty matter, and as we become more economical we shall utilize of what we now throw away. The germ of the corn kernel, once discarded in the manufacture of starch, now yields a popular table oil. From tomato seeds, one of the waste products of the canning factory, can be extracted 22% of an edible oil. Oats contain 7% of oil. From rapeseed the Japanese get 20,000 tons of oil a year. To the sources previously mentioned may be added pumpkin seeds, poppy seeds, raspberry seeds, tobacco seeds, cockleburs, hazelnuts, walnuts, beech nuts, and acorns. The oil-bearing seeds of the tropics are innumerable and will become increasingly essential to the inhabitants of northern lands. It was the realization of this that brought on the struggle of the great powers for the possession of tropical territory which, for years before, they did not think worth while raising a flag over. No country in the future can consider itself safe unless it has secure access to such sources. We had a sharp lesson in this during the war. Palm oil, it seems, is necessary for the manufacture of tin plate, an industry that was built up in the United States by the McKinley Tariff. The British possessions in West Africa were the chief source of palm oil and the Germans had the handling of it. During the war, the British government assumed control of the palm oil products of the British and German colonies and prohibited their export to other countries than England. Americans protested and beseeched, but in vain. The British held, quite correctly, that they needed all the oil they could get for food and lubrication and nitroglycerin. But the British also needed canned meat from America for their soldiers, and when it was at length brought to their attention that the packers could not ship meat unless they had cans and that cans could not be made without tin and that tin could not be made without palm oil, the British government consented to let us buy a little of their palm oil. The lesson is that of Voltaire's story Candide. Let us cultivate our own garden and plant a few palm trees in it, also rubber trees, but that is another story. The international struggle for oil led to the partition of the Pacific as the struggle for rubber led to the partition of Africa. Theodore Weber, as Stevenson says, harried the Samoans to get copra much as King Leopold of Belgium harried the Congolese to get caoutchouc. It was Weber who first fully realized that the South Sea Islands, formerly given over to cannibals, pirates, and missionaries, might be made immensely valuable through the cultivation of the coconut palms. When ripe, the coconut is split open and exposed to the sun, the meat dries up and shrivels and in this form, called copra, it can be cut out and shipped to the factory where the oil is extracted and refined. Weber, while German consul in Samoa, was also manager of what was locally known as the long-handled concern, Deutsche Handels- und Plantagen-Gesellschaft der Südsee Inseln zu Hamburg, a pioneer commercial and semi-official corporation that played a part in the Pacific somewhat like the British Hudson Bay Company in Canada or East India Company in Hindustan. Through the agency of this corporation on the start, Germany acquired a virtual monopoly of the transportation and refining of coconut oil and would have become the dominant power in the Pacific if she had not been checked by force of arms. In Apia Bay in 1889 and again in Manila Bay at 1898, an American fleet faced a German fleet ready for action while a British warship lay between. So we rescued the Philippines and Samoa from German rule, and in 1914 German power was eliminated from the Pacific. During the 10 years before the war, the production of copra in the German islands more than doubled, and this was only the beginning of the business. Now these islands have been divided up among Australia, New Zealand, and Japan, and these countries are planning to take care of the copra. But although we get no extension of territory from the war, we still have the Philippines and some of the Samoan Islands, and these are capable of great development. From her share of the Samoan Islands, Germany got $1 million worth of copra, and we might get more from ours. The Philippines now lead the world in the production of copra, but Java is a close second and Ceylon not far behind. If we do not look out, we will be beaten both by the Dutch and the British, for they are undertaking the cultivation of the coconut on a larger scale and in a more systematic way. According to an official bulletin of the Philippine government, a coconut plantation should bring in dividends ranging from 10 to 75% from the 10th to the 100th year. And this being printed in 1913 figured the price of copra at 3.5 cents, whereas it brought 4.5 cents in 1918, so the prospect is still more encouraging. The copra is half fat and can be cheaply shipped to America, where it can be crushed in the southern oil mills when they are not busy on cottonseed or peanuts. But even this cost of transportation can be reduced by extracting the oil in the islands and shipping it in bulk like petroleum in tank steamers. In the year ending June 1918, the United States imported from the Philippines 155 million pounds of coconut oil worth $18 million and 220 million pounds of copra worth $10 million. But this was about half of our total importations. The rest of it we had to get from foreign countries. Panama palms may give us a little relief from this dependence on foreign sources. In 1917, we imported 19 million whole coconuts from Panama valued at $700,000. A new form of fat that has rapidly come into our market is the oil of the soya or soybean. In 1918, we imported over 300 million pounds of soybean oil, mostly from Manchuria. The oil is used in manufacture of substitutes for butter, lard, cheese, milk, and cream, as well as for soap and paint. The soybean can be raised in the United States wherever corn can be grown and provides provender for man and beast. The soy meal left over after the extraction of the oil makes a good cattle food, and the fermented juice affords the soya sauce made familiar to us through the popularity of the chop suey restaurants. As meat and dairy products become scarcer and dearer, we shall become increasingly dependent upon the vegetable fats. We should therefore devise means of saving what we now throw away, raise as much as we can under our own flag, keep open avenues for our foreign supply, and encourage our cooks to make use of the new products invented by our chemists. End of chapter 11. End of section 12. Section 13. Chapter 12 of Creative Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, 2010. Creative Chemistry by Edwin Slosson. Chapter 12. Fighting with Fumes. The Germans opened the war using projectiles 17 inches in diameter. They closed it using projectiles 1/100 millionth of an inch in diameter, and the latter were more effective than the former. As the dimensions were reduced from molar to molecular, the battle became more intense, for when the Big Bertha had shot its bolt, that was the end of it. Whomever it hit was hurt, but after that the steel fragments of the shell lay on the ground harmless and inert. The men in the dugouts could hear the shells whistle overhead without alarm, but the poison gas could penetrate where the rifle ball could not. The malignant molecules seemed to search out their victims. They crept through the crevices of the subterranean shelters. They hunted for the pinholes in the face masks. They lay in wait for days in the trenches for the soldier's return as a cat watches at the hole of a mouse. The cannon ball could be seen and heard. The poison gas was invisible and inaudible, and sometimes even the chemical sense which nature has given man for his protection, the sense of smell, failed to give warning of the approach of the foe. The smaller the matter that man can deal with, the more he can get out of it. So long as man was dependent for power upon wind and water, his working capacity was very limited. But as soon as he passed over the border line from physics into chemistry and learned how to use the molecule, his efficiency in work and warfare was multiplied manifold. The molecular bombardment of the piston by steam or the gases of combustion runs his engines and propels his cars. The first man who wanted to kill another from a safe distance threw the stone by his arm's strength. David added to his arm the centrifugal force of a sling when he slew Goliath. The Romans improved on this by concentrating in a catapult the strength of a score of slaves and casting stone cannon balls to the top of the city wall. But finally man got closer to nature's secret and discovered that by loosing a swarm of gaseous molecules he could throw his projectile 75 miles and then, by the same force, burst it into flying fragments. There is no smaller projectile than the atom, unless our belligerent chemists can find a way of using the electron stream of the cathode ray. But this so far has figured only in the pages of our scientific romancers and has not yet appeared on the battlefield. If, however, man could tap the reservoir of subatomic energy, he need do no more work and would make no more war, for unlimited powers of construction and destruction would be at his command. The forces of the infinitesimal are infinite. The reason why a gas is so active is because it is so egoistic. Psychologically interpreted, a gas consists of particles having the utmost aversion to one another. Each tries to get as far away from every other as it can. There is no cohesive force, no attractive impulse, nothing to draw them together except the all too feeble power of gravitation. The hotter they get, the more they try to disperse, and so the gas expands. The gas represents the extreme of individualism as steel represents the extreme of collectivism. The combination of the two works wonders. A hot gas in a steel cylinder is the most powerful agency known to man, and by means of it he accomplishes his greatest achievements in peace or wartime. The projectile is thrown from the gun by the expansive force of the gases released from the powder, and when it reaches its destination it is blown to pieces by the same force. This is the end of it, if it is a shell of the old-fashioned sort, for the gases of combustion mingle harmlessly with the air of which they are normal constituents. But if it is a poison gas shell, each molecule as it is released goes off straight into the air with a speed twice that of the cannon ball and carries death with it. A man may be hit by a heavy piece of lead or iron and still survive, but an unweighable amount of lethal gas may be fatal to him. Most of the novelties of the war were merely extensions of what was already known. To increase the caliber of a cannon from 38 to 42 centimeters, or its range from 30 to 75 miles, does indeed make necessary a decided change in tactics, but it is not comparable to the revolution effected by the introduction of new weapons of unprecedented power, such as airplanes, submarines, tanks, high explosives, or poison gas. If any army had been as well equipped with these in the beginning as all armies were at the end, it might easily have won the war. That is to say, if the general staff of any of the powers had had the foresight and confidence to develop and practice these modes of warfare on a large scale in advance, it would have been irresistible against an enemy unprepared to meet them. But no military genius appeared on either side with sufficient courage and imagination to work out such schemes in secret before trying them out on a small scale in the open. Consequently, the enemy had fair warning and ample time to learn how to meet them, and the methods of defense developed concurrently with methods of attack. For instance, consider the motor fortresses to which Ludendorff ascribes his defeat. The British first sent out a few clumsy tanks against the German lines. Then they set about making a lot of stronger and livelier ones, but by the time these were ready the Germans had field guns to smash them, and chain fences with concrete posts to stop them. On the other hand, if the Germans had followed up their advantage when they first set the cloud of chlorine floating over the battlefield of Ypres, they might have won the war in the spring of 1915 instead of losing it in the fall of 1918. For the British were unprepared and unprotected against the silent death that swept down upon them on the 22nd of April, 1915. What happened then is best told by Sir Arthur Conan Doyle in his History of the Great War. From the base of the German trenches, over a considerable length, there appeared jets of whitish vapor, which gathered and swirled until they settled into a definite low cloud bank, greenish brown below and yellow above, where it reflected the rays of the sinking sun. This ominous bank of vapor, impelled by a northern breeze, drifted swiftly across the space which separated the two lines. The French troops, staring over the top of their parapet at this curious screen which ensured them a temporary relief from fire, were observed suddenly to throw up their hands, to clutch at their throats, and to fall at the ground in the agonies of asphyxiation. Many lay where they had fallen, while their comrades, absolutely helpless against this diabolical agency, rushed madly out of the mephitic mist and made for the rear, overrunning the lines of trenches behind them. Many of them never halted until they had reached Ypres, while others rushed westwards and put the canal between themselves and the enemy. The Germans, meanwhile, advanced and took possession of the successive lines of trenches, terminated only by the dead garrisons, whose blackened faces, contorted figures, and lips fringed with the blood and foam from their bursting lungs showed the agonies in which they had died. Some thousands of stupefied prisoners, 8 batteries of French field guns, and 4 British 4.7s, which had been placed in a wood behind the French position, were the trophies won by this disgraceful victory. Under the shattering blow which they had received, a blow particularly demoralizing to African troops with their fears of magic and the unknown. It was impossible to rally them effectually until the next day. It is to be remembered in explanation of this disorganization that it was the first experience of these poison tactics, and that the troops engaged received the gas in a very much more severe form than our own men on the right of Langemarck. For a time there was a gap 5 miles broad in the front of the position of the Allies, and there were many hours during which there was no substantial force between the Germans and Ypres. They wasted their time, however, in consolidating their ground, and the chance of a great coup passed forever. They had sold their souls as soldiers, but the devil's price was a poor one. Had they had a corps of cavalry ready and pushed them through the gap, it would have been the most dangerous moment of the war. A deserter had come over from the German side a week before, and told them that cylinders of poison gas had been laid in the front trenches, but no one believed him or paid any attention to his tale. War was then, in the Englishman's opinion, a gentleman's game, the royal sport, and poison was prohibited by the Hague rules. But the Germans were not playing the game according to the rules, so the British soldiers were strangled in their own trenches, and fell easy victims to the advancing foe. Within half an hour after the gas was turned on, 80% of the opposing troops were knocked out. The Canadians, with wet handkerchiefs over their faces, closed in to stop the gap, but if the Germans had been prepared for such success, they could have cleared the way to the coast. But after such trials the Germans stopped the use of free chlorine and began the preparation of more poisonous gases. In some way that may not be revealed till the secret history of the war is published. The German intelligence department obtained a copy of the lecture notes of the instructions to the German staff, giving details of the new system of gas warfare to be started in December. Among the compounds named was phosgene, a gas so lethal that 1 part in 10,000 of air may be fatal. The antidote for it is hexamethylene tetramine. This is not something the soldier, or anybody else, is accustomed to carry around with him, but the British having had a chance to cram up in advance on the stolen lecture notes, were ready with gas helmets soaked in the reagent with the long name. The Germans rejoiced when gas bombs took the place of bayonets, because this was a field in which intelligence counted for more than brute force, and in which, therefore, they expected to be supreme. As usual, they were right in their major premise, but wrong in their conclusion, owing to the egoism of their implicit minor premise. It does indeed give the advantage to skill and science, but the Germans were beaten at their own game, for by the end of the war the United States was able to turn out toxic gases at a rate of 200 tons a day, while the output of Germany or England was only about 30 tons. A gas plant was started at Edgewood, Maryland, in November, 1917. By March it was filling shell, and before the war put a stop to its activities in the fall it was producing 1.3 million pounds of chlorine, 1 million pounds of chlorpicrin, 1.3 million pounds of phosgene, and 70,000 pounds of a mustard gas a month. Chlorine, the first gas used, is unpleasantly familiar to everyone who has entered a chemical laboratory or who has smelled the breath of bleaching powder. It is a greenish yellow gas made from common salt. The Germans employed it at Ypres by laying cylinders of the liquefied gas in the trenches, about a yard apart, and running a lead discharge pipe over the parapet. When the stopcocks are turned, the gas streams out, and since it is 2½ times as heavy as air, it rolls over the ground like a noisome mist. It works best when the ground slopes gently down toward the enemy and when the wind blows in that direction at a rate between 4 and 12 miles an hour. But the wind, being strictly neutral, may change its direction without warning, and then the gases turn back in their flight and attack their own side, something that rifle bullets have never been known to do. Because free chlorine would not stay put and was dependent on the favor of the wind for its effect, it was later employed, not as an elemental gas, but in some volatile liquid that could be fired in a shell and so released at any particular point far back of the front trenches. The most commonly used of these compounds was phosgene, which, as the reader can see by inspection of its formula, COCl2, consists of chlorine combined with carbon monoxide, the cause of deaths from illuminating gas. These two poisonous gases, chlorine and carbon monoxide, when mixed together, will not readily unite, but if a ray of sunlight falls upon the mixture they combine at once. For this reason John Davy, who discovered the compound over 100 years ago, named it phosgene, that is, produced by light. The same roots recur in hydrogen, so named because it is produced from water, and phosphorus because it is a light bearer. In its modern manufacture, the catalyzer or instigator of the combination is not sunlight but porous carbon. This is packed in iron boxes 8 feet long, through which the mixture of the two gases was forced. Carbon monoxide may be made by burning coke with a supply of air insufficient for complete combustion, but in order to get the pure gas necessary for the phosgene common air was not used, but instead pure oxygen extracted from it by a liquid air plant. Phosgene is a gas that may be condensed easily to a liquid by cooling it down to 46 degrees Fahrenheit. A mixture of 3/4 chlorine with 1/4 phosgene has been found most effective. By itself, phosgene has an inoffensive odor somewhat like green corn, and so may fail to arouse apprehension until a toxic concentration is reached, but even small doses have such an effect upon the heart action for days afterwards that a slight exertion may prove fatal. The compound manufactured in largest America was chlorpicrin. This, like the others, is not so unfamiliar as it seems. As may be seen from its formula, CCl3NO2, it is formed by joining the nitric acid radical, NO2, found in all explosives, with the main part of chloroform, HCCl3. This is not quite so poisonous as phosgene, but it has the advantage that it causes nausea and vomiting. The soldier so affected is forced to take off his gas mask and then may fall victim to more toxic gases sent over simultaneously. Chlorpicrin is a liquid and is commonly loaded in the shell or bomb with 20% of tin chloride, which produces dense white fumes that go through gas masks. It is made from picric acid, trinitrophenol, one of the best known of the high explosives, by treatment with chlorine. The chlorine is obtained, as it is in the household, from common bleaching powder, or chloride of lime. This is mixed with water to form a cream in a steel still 18 feet high and 8 feet in diameter. A solution of calcium picrate, that is, the lime salt of picric acid, is pumped in, and as the reaction begins the mixture heats up and the chlorpicrin distills over with the steam. When the distillate is condensed the chlorpicrin, being the heavier liquid, settles out under the layer of water and may be drawn off to fill the shell. Much of what a student learns in the chemical laboratory he is apt to forget in later life if he does not follow it up. But there are two gases that he always remembers, chlorine and hydrogen sulfide. He is lucky if he has escaped being choked by the former or sickened by the latter. He can imagine what the effect would be if two offensive fumes could be combined without losing their offensive features. Now a combination something like this is the so-called mustard gas, which is not a gas and is not made from mustard. But it is easily gasified, and oil of mustard is about as near as nature dare come to making such sinful stuff. It was first made by Guthrie, an Englishman, in 1860, and rediscovered by a German chemist, Victor Meyer, in 1886, but he found it so dangerous to work with that he abandoned the investigation. Nobody else cared to take it up, for nobody could see any use for it. So it remained in innocuous desuetude, a mere name in Beilstein's dictionary, together with the thousands of other organic compounds that have been invented and never utilized. But on July 12, 1917, the British holding the line at Ypres were besprinkled with this villainous substance. Its success was so great that the Germans henceforth made it their main reliance, and soon the Allies followed suit. In one offensive of 10 days, the Germans are said to have used 1,000,000 shells containing 2,500 tons of mustard gas. The making of so dangerous a compound on a large scale was one of the most difficult tasks set before the chemists of this and other countries, yet it was successfully solved. The raw materials are chlorine, alcohol, and sulfur. The alcohol is passed with steam through a vertical iron tube filled with kaolin and heated. This converts the alcohol into a gas known as ethylene, C2H4. Passing a stream of chlorine gas into a tank of melted sulfur produces sulfur monochloride, and this treated with the ethylene makes the mustard. The final reaction was carried on at the Edgewood Arsenal in 7 airtight tanks or reactors, each having a capacity of 30,000 pounds. The ethylene gas being led into the tank and distributed through the liquid sulfur chloride by porous blocks or fine nozzles, the two chemicals combine to form what is officially named dichlor-diethyl sulfide, ClC2H4SC2H4Cl. This, however, is too big a mouthful, so even the chemists were glad to fall in with the commonality and call it mustard gas. The effectiveness of mustard depends on its persistence. It is a stable liquid, evaporating slowly and not easily decomposed. It lingers about trenches and dugouts and impregnates soil and cloth for days. Gas masks do not afford complete protection, for even if they are impenetrable they must be taken off sometime, and the gas lies in wait for that time. In some cases the masks were worn continuously for 12 hours after the attack, but when they were removed the soldiers were overpowered by the poison. A place may seem to be free from it, but when the sun heats up the ground the liquid volatilizes and the vapor soaks through the clothing. As the men become warmed up by work their skin is blistered, especially under the armpits. The mustard acts like steam, producing burns that range from a mere reddening to serious ulcerations, always painful and incapacitating, but if treated promptly in the hospital rarely cause death or permanent scars. The gas attacks the eyes, throat, nose, and lungs, and may lead to bronchitis or pneumonia. It was found necessary at the front to put all the clothing of the soldiers into the sterilizing ovens every night to remove all traces of mustard. General Johnson and his staff in the 77th Division were poisoned in their dugouts because they tried to alleviate the discomfort of their camp cots by bedding taken from a neighboring village that had been shelled the day before. Of the 925 cases requiring medical attention at the Edgewood Arsenal, 674 were due to mustard. During the month of August, 3.5% of the mustard plant force were sent to the hospital each day on the average. But the record of the Edgewood Arsenal is a striking demonstration of what can be done in the prevention of industrial accidents by the exercise of scientific prudence. In spite of the fact that from 3 to 11,000 men were employed at the plant for the year 1918 and turned out some 20,000 tons of the most poisonous gases known to man, there were only 3 fatalities and not a single case of blindness. Besides the 4 toxic gases previously described, chlorine, phosgene, chlorpicrin, and mustard, various other compounds have been made and many others might be made. A list of those employed in the present war enumerates 30, among them compounds of bromine, arsenic, and cyanogen that may prove more formidable than any so far used. American chemists kept very mum during the war, but occasionally one could not refrain from saying, "If the Kaiser knew what I know, he would surrender unconditionally by telegraph." No doubt the science of chemical warfare is in its infancy, and every foresighted power has concealed weapons of its own in reserve. One deadly compound, whose identity has not yet been disclosed, is known as lewisite, from Professor Lewis of Northwestern, who is manufacturing it at the rate of 10 tons a day in the Mousetrap Stockade near Cleveland. Throughout the history of warfare, the art of defense has kept pace with the art of offense, and the courage of man has never failed, no matter to what new danger he was exposed. As each new gas employed by the enemy was detected, it became the business of our chemists to discover some method of absorbing or neutralizing it. Porous charcoal, best made from such dense wood as coconut shells, was packed in the respirator box together with layers of such chemicals as will catch the gases to be expected. Charcoal absorbs large quantities of any gas. Soda lime and potassium permanganate and nickel salts were among the neutralizers used. The mask is fitted tightly about the face or over the head with rubber. The nostrils are kept closed with a clip, so breathing must be done through the mouth and no air can be inhaled except that passing through the absorbent cylinder. Men within 5 miles of the front were required to wear the masks slung on their chests so they could be put on within 6 seconds. A well-made mask with a fresh box afforded almost complete immunity for a time, and the soldiers learned within a few days to handle their masks adroitly. So the problem of defense against this new offensive was solved satisfactorily, while no such adequate protection against the older weapons of bayonet and shrapnel has yet been devised. Then the problem of the offense was to catch the opponent with his mask off, or to make him take it off. Here the lachrymators and sternutators, the tear gases and the sneeze gases, came into play. Phenylcarbylamine chloride would make the bravest soldier weep on the battlefield with the abandonment of a Greek hero. Diphenylchloroarsenine would get him sneezing. The Germans alternated these with diabolical ingenuity so as to catch us unawares. Some shells gave off voluminous smoke or a vile stench without doing much harm, but by the time our men got used to these and grew careless about their masks, a few shells of some extremely poisonous gas were mixed with them. The ideal gas for belligerent purposes would be odorless, colorless, and invisible, toxic even when diluted by a million parts of air, not set on fire or exploded by the detonator of the shell, not decomposed by water, not readily absorbed, stable enough to stand storage for 6 months, and capable of being manufactured by the thousands of tons. No one gas will serve all aims. For instance, phosgene being very volatile and quickly dissipated is thrown into trenches that are soon to be taken, while mustard gas being very tenacious could not be employed in such a case, for the trenches could not be occupied if they were captured. The extensive use of poison gas in warfare by all the belligerents is a vindication of the American protest at the Hague Conference against its prohibition. At the first conference of 1899, Captain Mahan argued very sensibly that gas shells were no worse than other projectiles and might indeed prove more merciful, and that it was illogical to prohibit a weapon merely because of its novelty. The British delegates voted with the Americans in opposition to the clause. The contracting parties agree to abstain from the use of projectiles, the sole object of which is the diffusion of asphyxiating or deleterious gases. But both Great Britain and Germany later agreed to the provision. The use of poison gas by Germany without warning was therefore an act of treachery and a violation of her pledge, but the United States has consistently refused to bind herself to any such restriction. The facts reported by General Amos A. Fries, in command of the overseas branch of the American Chemical Warfare Service, gave ample support to the American contention at The Hague. Out of 1,000 gas casualties there are from 30 to 40 fatalities, while out of 1,000 high explosive casualties the number of fatalities runs from 200 to 250. While exact figures are as yet not available concerning the men permanently crippled or blinded by high explosives, one has only to witness the debarkation of a shipload of troops to be convinced that the number is very large. On the other hand, there is, so far as known at present, not a single case of permanent disability or blindness among our troops due to gas, and this in face of the fact that the Germans used relatively large quantities of this material. In the light of these facts, the prejudice against the use of gas must gradually give way, for the statement made to the effect that its use is contrary to the principles of humanity will apply with far greater force to the use of high explosives. As a matter of fact, for certain purposes toxic gas is an ideal agent. For example, it is difficult to imagine any agent more effective or more humane that may be used to render an opposing battery ineffective or to protect retreating troops. Captain Mahan's argument at The Hague against the proposed prohibition of poison gas is so cogent and well expressed that it has been quoted in treatises on international law ever since. The reasons were, briefly: 1. that no shell emitting such gases is as yet in practical use or has gone adequate experiment. Consequently, a vote taken now would be taken in ignorance of the facts as to whether the results would be of a decisive character or whether injury in excess of that necessary to attain the end of warfare, the immediate disabling of the enemy, would be inflicted. 2. That the reproach of cruelty and perfidy addressed against these supposed shells was equally uttered formerly against firearms and torpedoes, both of which are now employed without scruple. Until we know the effects of such asphyxiating shells, there was no saying whether they would be more or less merciful than missiles now permitted. That it was illogical, and not demonstrably humane, to be tender about asphyxiating men with gas when all are prepared to admit that it was allowable to blow the bottom out of an ironclad at midnight, throwing 400 or 500 into the sea to be choked by water with scarcely the remotest chance of escape. As Captain Mahan says, the same objection has been raised at the introduction of each new weapon of war, even though it proved to be no more cruel than the old. The modern rifle ball, swift and small and sterilized by heat, does not make so bad a wound as the ancient sword and spear. But we all remember how gunpowder was regarded by the dandies of Hotspur's time. And it was great pity, so it was, this villainous saltpeter should be digged out of the bowels of the harmless earth, which many a good tall fellow had destroyed, so cowardly, and but for these vile guns, he would himself have been a soldier. The real reason for the instinctive aversion manifested against any new arm or mode of attack is that it reveals to us the intrinsic horror of war. We naturally revolt against premeditated homicide, but we have become so accustomed to the sword and latterly to the rifle that they do not shock us as they ought when we think of what they are made for. The Constitution of the United States prohibits the infliction of cruel and unusual punishments. The two adjectives were apparently used almost synonymously, as though any unusual punishment were necessarily cruel, and so indeed it strikes us, but our ingenious lawyers were able to persuade the courts that electrocution, although unknown to the fathers and undeniably unusual, was not unconstitutional. Dum-dum bullets are rightfully ruled out because they inflict frightful and often incurable wounds, and the aim of humane warfare is to disable the enemy, not permanently to injure him. In spite of the opposition of the American and British delegates, the first Hague Conference adopted the clause, "The contracting powers agree to abstain from the use of projectiles the sole object of which is the diffusion of asphyxiating or deleterious gases." The word sole, unique, which appears in the original French text of the Hague Convention, is left out of the official English translation. This is a strange omission considering that the French and British defended their use of explosives which diffuse asphyxiating and deleterious gases on the ground, that this was not the sole purpose of the bombs, but merely an accidental effect of the nitric powder used. The Hague Congress of 1907 placed in its rules for war, "It is expressly forbidden to employ poisons or poisonous weapons." But such attempts to rule out new and more effective means of warfare are likely to prove futile in any serious conflict, and the restriction gives the advantage to the most unscrupulous side. We Americans, if ever we give our assent to such an agreement, would of course keep it, but our enemy, whoever he may be in the future, will be, as he always has been, utterly without principle, and will not hesitate to employ any weapon against us. Besides, as the Germans held, chemical warfare favors the enemy that is most intelligent, resourceful and disciplined, and the nation that stands highest in science and industry. This advantage, let us hope, will be on our side. End of chapter 12. End of section 13. Section 14, Chapter 13, of Creative Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, 2010. Creative Chemistry by Edwin E. Slosson. Chapter 13. Products of the Electric Furnace. The control of man over the materials of nature has been vastly enhanced by the recent extension of the range of temperature at his command. When Fahrenheit stuck the bulb of his thermometer into a mixture of snow and salt, he thought he had reached the nadir of temperature, so he scratched a mark on the tube where the mercury stood and called it zero. But we know that absolute zero, the total absence of heat, is 459 of Fahrenheit's degrees lower than his 0 point. The modern scientist can get close to that lowest limit by making use of the cooling by the expansion principle. He first liquefies air under pressure and then releasing the pressure allows it to boil off. A tube of hydrogen immersed in the liquid air as it evaporates is cooled down until it can be liquefied. Then the boiling hydrogen is used to liquefy helium, and as this boils off it lowers the temperature to within 3 or 4 degrees of absolute zero. The early metallurgist had no hotter a fire than he could make by blowing charcoal with a bellows. This was barely enough for the smelting of iron. But by the bringing of two carbon rods together, as in the electric arc light, we can get enough heat to volatilize the carbon at the tips, and this means over 7,000 degrees Fahrenheit. By getting a pressure of 20 atmospheres into the arc light, we can raise it to perhaps 14,000 degrees, which is 3,000 degrees hotter than the sun. This gives the modern man a working range of about 14,500 degrees, so it is no wonder that he can perform miracles. When a builder wants to make an old house over into a new one, he takes it apart brick by brick and stone by stone. Then he puts them together in such new fashion as he likes. The electric furnace enables the chemist to take his materials apart in the same way. As the temperature rises, the chemical and physical forces that hold a body together gradually weaken. First the solid loosens up and becomes a liquid. Then this breaks bonds and becomes a gas. Compounds break up into their elements. The elemental molecules break up into their component atoms, and finally these begin to throw off corpuscles of negative electricity 1,800 times smaller than the smallest atom. These electrons appear to be the building stones of the universe. No indication of any smaller units has been discovered, although we need not assume that in the electron science has delivered what has been called this ultim atom. The Greeks called the elemental particles of matter atoms because they esteemed them indivisible, but now in the light of the X-ray we can witness the disintegration of the atom into electrons. all the chemical and physical properties of matter, except perhaps weight, seem to depend upon the number and movement of the negative and positive electrons, and by their rearrangement one element may be transformed into another. So the electric furnace, where the highest attainable temperature is combined with the divisive and directive force of the current, is a magical machine for accomplishment of the metamorphoses desired by the creative chemist. 100 years ago Davy, by dipping the poles of his battery into melted soda lye, saw forming on one of them a shining globule like quicksilver. It was the metal sodium, never before seen by man. Nowadays this process of electrolysis, electron loosening, is carried out daily by the ton at Niagara. The reverse process, electrosynthesis, electric combining, is equally simple and even more important. By passing a strong electric current through a mixture of lime and coke, the metal calcium disengages itself from the oxygen of the lime and attaches itself to the carbon. Or, to put it briefly, CaO lime plus 3C coke goes to CaC2 calcium carbide plus CO carbon monoxide. This reaction is of peculiar importance because it bridges the gulf between the organic and inorganic worlds. It was formerly supposed that the substances found in plants and animals, mostly complex compounds of carbon, hydrogen, and oxygen, could only be produced by vital forces. If this were true, it meant that chemistry was limited to the mineral kingdom and to the extraction of such carbon compounds as happen to exist readily formed in the vegetable and animal kingdoms. But fortunately this barrier to human achievement proved purely illusory. The organic field, once man had broken into it, proved easier to work in than the inorganic. But it must be confessed that man is dreadfully clumsy about it yet. He takes a 1,000 horsepower engine and an electric furnace at several thousand degrees to get carbon into combination with hydrogen, while the little green leaf in the sunshine does it quietly without getting hot about it. Evidently man is working as wastefully as when he used 1,000 slaves to drag a stone to the pyramid or burn down a house to roast a pig. Not until his laboratory is as cool and calm and comfortable as the forest and the field can the chemist call himself completely successful. But in spite of his clumsiness, the chemist is actually making things that he wants and cannot get elsewhere. The calcium carbide that he manufactures from inorganic material serves as the raw material for producing all sorts of organic compounds. The electric furnace was first employed on a large scale by the Cowles Electric Smelting and Aluminum Company at Cleveland in 1885. On the dump were found certain lumps of porous gray stone which, dropped into water, gave off a gas that exploded at touch of a match with a splendid bang and flare. This gas was acetylene, and we can represent the reaction thus: CaC2 calcium carbide plus 2H2O water goes to C2H2 acetylene plus CaO2H2 slaked lime. Calcium carbide added to water gives acetylene and slaked lime. We are all familiar with this reaction now, for it is acetylene that gives the dazzling light of the automobiles and of the automatic signal buoys of the seacoast. When burned with pure oxygen instead of air, it gives the hottest of chemical flames, hotter even than the oxy-hydrogen blowpipe. For although a given weight of hydrogen will give off more heat when it burns than carbon will, Yet acetylene will give off more heat than either of its elements or both of them when they are separate. This is because acetylene has stored up heat in its formation instead of giving it off as in most reactions, or to put it in chemical language, acetylene is an endothermic compound. It has required energy to bring the H and the C together. Therefore, it does not require energy to separate them. But on the contrary, energy is released when they are separated. That is to say, acetylene is explosive not only when mixed with air as coal gas is, but by itself. Under a suitable impulse, acetylene will break up into its original carbon and hydrogen with great violence. It explodes with twice as much force without air as ordinary coal gas with air. It forms an explosive compound with copper, so it has to be kept out of contact with brass tubes and stopcocks. But compressed in steel cylinders and dissolved in acetone, it is safe and commonly used for welding and melting. It is a marvelous, though not an unusual sight on city streets to see a man with blue glasses on, cutting down through a steel rail with an oxyacetylene blowpipe as easily as a carpenter saws off a board. With such a flame he can carve out a pattern in a steel plate in a way that reminds me of the days when I used to make brackets with a scroll saw out of cigar boxes. The torch will travel through a steel plate an inch or two thick at a rate of 6 to 10 inches a minute. The temperatures attainable with various fuels in the compound blowpipe are said to be: acetylene with oxygen 7,878 Fahrenheit, hydrogen with oxygen 6,785 degrees Fahrenheit, coal gas with oxygen 6,575 Fahrenheit, gasoline with oxygen 5,788 Fahrenheit. If we compare the formula of acetylene, C2H2, with that of ethylene, C2H4, or with ethane, C2H6, we see that acetylene could take on 2 or 4 more atoms. It is evidently what the chemists call an unsaturated compound, one that has not reached its limit of hydrogenation. It is therefore a very active and energetic compound, ready to pick up on the slightest instigation hydrogen or oxygen or chlorine or any other elements that happen to be handy. This is why it is so useful as a starting point for synthetic chemistry. To build up from this simple substance, acetylene, the higher compounds of carbon and oxygen, it is necessary to call in the aid of that mysterious agency, the catalyst. Acetylene is not always acted upon by water, as we know, for we see it bubbling up through the water when prepared from the carbide. But if to the water be added a little acid and a mercury salt, the acetylene gas will unite with the water, forming a new compound, acetaldehyde. We can show the change most simply in this fashion: C2H2, acetylene, added to H2O, water, forms C2H4O, acetaldehyde. Acetaldehyde is not of much importance in itself, but it is useful as a transition. If its vapor mixed with hydrogen is passed over finely divided nickel, serving as a catalyst, the two unite and we have alcohol, according to this reaction. C2H4O, acetaldehyde, added to H2, hydrogen, forms C2H6O, alcohol. Alcohol we are all familiar with, some of us too familiar, but the prohibition laws will correct that. The point to be noted is that the alcohol we have made from such unpromising materials as limestone and coal is exactly the same alcohol as is obtained by the fermentation of fruits and grains by the yeast plant as in wine and beer. It is not a substitute or imitation. It is not the wood spirits, methyl alcohol, CH4O, produced by the destructive distillation of wood, equally serviceable as a solvent or fuel, but undrinkable and poisonous. Now, as we all know, cider and wine when exposed to the air gradually turn into vinegar. That is, by the growth of bacteria, the alcohol is oxidized to acetic acid. We can, if we like, dispense with the bacteria and speed up the process by employing a catalyst. Acetaldehyde, which is halfway between alcohol and acid, may also be easily oxidized to acetic acid. The relationship is readily seen by this. Alcohol C2H6O forms CC2H4O. Acetaldehyde forms C2H4O3, acetic acid. Acetic acid, familiar to us in a diluted and flavored form as vinegar, is when concentrated of great value in industry, especially as a solvent. I have already referred to its use in combination with cellulose as a dope for varnishing airplane canvas or making non-inflammable film for motion pictures. Its combination with lime, calcium acetate, when heated gives acetone, which, as may be seen from its formula C3H6O, is closely related to the other compounds we have been considering, but it is neither an alcohol nor an acid. It is extensively employed as a solvent. Acetone is not only useful for dissolving solids, but it will under pressure dissolve many times its volume of gaseous acetylene. This is a convenient way of transporting and handling acetylene for lighting or welding. If instead of simply mixing the acetone and acetylene in a solution we combine them chemically, we can get isoprene, which is the mother substance of ordinary India rubber. From acetone also is made the war rubber of the Germans, methyl rubber, which I have mentioned in a previous chapter. The Germans had been getting about half their supply of acetone from American acetate of lime, and this was of course shut off. That which was produced in Germany by the distillation of beech wood was not even enough for the high explosives needed at the front. So the Germans resorted to rotting potatoes, or rather let us say, since it sounds better, to the cultivation of Bacillus macerans. This particular bacillus converts the starch of the potato into 2/3 alcohol and 1/3 acetone. But soon potatoes got too scarce to be used up in this fashion, so the Germans turned to calcium carbide as a source of acetone, and before the war ended they had a factory capable of manufacturing 2,000 tons of methyl rubber a year. This shows the advantage of having several strings to a bow. The reason why acetone is such an active and acquisitive thing the chemist explains, or rather expresses, by picturing its structure in this shape: H single bond C, triple bond C, single bond H. Now the carbon atoms are holding each other's hands because they have nothing else to do. There are no other elements around to hitch onto. But the two carbons of acetylene readily loosen up, and keeping the connection between them by a single bond reach out in this fashion with their two disengaged arms and grab whatever alien atoms happen to be in the vicinity. H single bond C with two open bonds, single bond C with two open bonds, single bond H. Carbon atoms belong to the quadrumani like the monkeys, so they are peculiarly fitted to forming chains and rings. This accounts for the variety and complexity of the carbon compounds. So when acetylene gas mixed with other gases is passed over a catalyst, such as a heated mass of iron ore or clay, hydrates or silicates of iron or aluminum, it forms all sorts of curious combinations. In the presence of steam we may get such simple compounds as acetic acid, acetone, and the like. But when three acetylene molecules join to form a ring of six carbon atoms, we get compounds of the benzene series, such as were described in the chapter on the coal tar colors. If ammonia is mixed with acetone, we get many rings with the nitrogen atom in place of one of the carbons, like the pyridins and quinolines, pungent bases such as are found in opium and tobacco. Or if hydrogen sulfide is mixed with the acetylene, we may get thiophenes, which have sulfur in the ring. So, starting with the simple combination of two atoms of carbon with two of hydrogen, we can get directly by this single process some of the most complicated compounds of the organic world, as well as many others not found in nature. In the development of the electric furnace America played a pioneer part. Provost Smith, of the University of Pennsylvania, who is the best authority on the history of chemistry in America, claims for Robert Hare, a Philadelphia chemist born in 1781, the honor of constructing the first electrical furnace. With this crude apparatus, and with no greater electromotive force than could be attained from a voltaic pile, he converted charcoal into graphite, volatilized phosphorus from its compounds, isolated metallic calcium, and synthesized calcium carbide. It is to Hare also that we owe the invention in 1801 of the oxyhydrogen blowpipe, which nowadays is used with acetylene as well as hydrogen. With this instrument he was able to fuse strontia and volatilize platinum. But the electrical furnace could not be used on a commercial scale until the dynamo replaced the battery as a source of electricity. The industrial development of the electrical furnace centered about the search for a cheap method of preparing aluminum. This is the metallic base of clay and therefore is common enough. But clay, as we know from its use in making porcelain, is very infusible and difficult to decompose. 60 years ago aluminum was priced at $140 a pound, but one would have had difficulty in buying such a large quantity as a pound at any price. At international expositions a small bar of it might be seen in a case labeled "Silver from Clay." Mechanics were anxious to get the new metal, for it was light and untarnishable, but the metallurgist could not furnish it to them at a low enough price. In order to extract it from clay, a more active metal, sodium, was essential, but sodium also was rare and expensive. In those days a professor of chemistry used to keep a little stick of it in a bottle under kerosene, and once a year he whittled off a piece the size of a pea and threw it into water to show the class how it sizzled and gave off hydrogen. The way to get cheaper aluminum was, it seemed, to get cheaper sodium, and Hamilton Young Castner set himself at this problem. He was a Brooklyn boy, a student at Chandler's at Columbia. You can see the bronze tablet in his honor at the entrance of Havemeyer Hall. In 1886 he produced metallic sodium by mixing caustic soda with iron and charcoal in an iron pot and heating in a gas furnace. Before this experiment sodium sold at $2 a pound. After it Sodium sold at 20 cents a pound. But although Castner had succeeded in his experiment, he was defeated in his object. For while he was perfecting the sodium process for making aluminum, the electrolytic process for getting aluminum directly was discovered in Oberlin. So the $250,000 plant of the Aluminum Company Limited that Castner had got erected at Birmingham, England, did not make aluminum at all, but produced sodium for other purposes instead. Castner then turned his attention to the electrolytic method of producing sodium by the use of power at Niagara Falls Electric Power. Here in 1894 he succeeded in separating common salt into its component elements, chlorine and sodium, by passing the electric current through brine and collecting the sodium in the mercury floor of the cell. The sodium by the action of water goes into caustic soda. Nowadays sodium and chlorine and their components are made in enormous quantities by the decomposition of salt. The United States government in 1918 procured nearly 4,000,000 pounds of chlorine for gas warfare. The discovery of the electrical process of making aluminum that displaced the sodium method was due to Charles M. Hall. He was the son of a Congregational minister and as a boy took a fancy to chemistry through happening upon an old textbook of that science in his father's library. He never knew who the author was, for the cover and title page had been torn off. The obstacle in the way of the electrolytic production of aluminum was, as I have said, because its compounds were so hard to melt that the current could not pass through. In 1886, when Hall was 22, he solved the problem in the laboratory of Oberlin College with no other apparatus than a small crucible, a gasoline burner to heat it with and a galvanic battery to supply the electricity. He found that a Greenland mineral known as cryolite, a double fluoride of sodium and aluminum, was readily fused and would dissolve aluminum oxide. When an electric current was passed through the melted mass, the metal aluminum would collect at one of the poles. In working out the process and defending his claims, Hall used up all his own money, his brother's, and his uncle's, but he won out in the end, and Judge Taft held that his patent had priority over the French claim of Hérault. On his death, a few years ago, Hall left his large fortune to his alma mater, Oberlin. Two other young men from Ohio, Alfred and Eugene Cowles, with whom Hall was for a time associated, were the first to develop the wide possibilities of the electric furnace on a commercial scale. In 1885 they started the Cowles Electric Smelting and Aluminum Company at Lockport, New York, using Niagara power. The various aluminum bronzes made by absorbing the electrolyzed aluminum in copper attracted immediate attention by their beauty and usefulness in electrical work, and later the company turned out other products besides aluminum, such as calcium carbide, phosphorus, and carborundum. They got carborundum as early as 1885 but miscalled it crystallized silicon. So its introduction was left to E. A. Acheson, who was a graduate of Edison's laboratory. In 1891 he packed clay and charcoal into an iron ball, connected it to a dynamo, and stuck into the mixture an electric light carbon connected to the other pole of the dynamo. When he pulled out the rod he found its end encrusted with glittering crystals of an unknown substance. They were blue and black and iridescent, exceedingly hard and very beautiful. He sold them at first by the carat at a rate that would amount to $560 a pound. They were as well worth buying as diamond dust, but those who purchased them must have regretted it, for much finer crystals were soon on sale at 10 cents a pound. The mysterious substance turned out to be a compound of carbon and silicon, the simplest possible compound, one atom of each, CSi. Acheson set up a factory at Niagara where he made it in 10-ton batches. The furnace consisted simply of a brick box 15 feet long and 7 feet wide and deep, with big carbon electrodes at the end. Between them was packed a mixture of coke to supply the carbon, sand to supply the silicon, sawdust to make the mass porous, and salt to make it fusible. The substance thus produced at Niagara Falls is known as carborundum, south of the American-Canadian boundary, and as crystolon, north of this line, as carbolon by another firm, and as silicon carbide by chemists the world over. Since it is next to the diamond in hardness, it takes off metal faster than emery, aluminum oxide, using less power and wasting less heat in futile fireworks. It is used for grindstones of all sizes, including those the dentist uses on your teeth. It has revolutionized shop practice, for articles can be ground into shape better and quicker than they can be cut. What is more, the artificial abrasives do not injure the lungs of the operatives like sandstone. The output of artificial abrasives in the United States and Canada for 1917 was silicon carbide 8,323 tons at $1,074,152, 48,463 tons, $6,969,387. A new use for carborundum was found during the war when Uncle Sam assumed the role of Jove as cloud compeller. Acting on carborundum with chlorine, also, you remember, a product of electrical dissolution, the chlorine displaces the carbon, forming silicon tetrachloride, SiCl4, a colorless liquid resembling chloroform. When this comes in contact with moist air, it gives off thick, white fumes, for water decomposes it, giving a white powder, silicon hydroxide, and hydrochloric acid. If ammonia is present, the acid will unite with it, giving further white fumes of the salt, aluminum chloride. So a mixture of 2 parts of silicon chloride with 1 part of dry ammonia was used in the war to produce smoke screens for the concealment of the movements of troops, batteries, and vessels, or put in shells, so the outlook could see where they burst and so get the range. Titanium tetrachloride, a similar substance, proved 50% better than silicon, but phosphorus, which also we get from the electric furnace, was the most effective mistifier of all. Before the introduction of the artificial abrasives, fine grinding was mostly done by emery, which is an impure form of aluminum oxide found in nature. A purer form is made from the mineral bauxite by driving off its combined water. Bauxite is the ore from which is made the pure aluminum oxide used in the electric furnace for the production of metallic aluminum. Formerly, we imported a large part of our bauxite from France, but when the war shut off this source, we developed our domestic fields in Arkansas, Alabama, and Georgia, and these are now producing 500,000 tons a year. Bauxite simply fused in the electric furnace makes a better abrasive than the natural emery or corundum, and it is sold for this purpose under the name of aloxite, alundum, exolon, lyonite, or coralox. When the fused bauxite is worked up with a bonding material into crucibles or muffles and baked in a kiln, it forms the alundum refractory ware. Since alundum is porous and not attacked by acids, it is used for filtering hot and corrosive liquids that would eat up filter paper. Carborundum or crystolon is also made up into refractory ware for high temperature work. When the fused mass of the carborundum furnace is broken up, there is found surrounding the carborundum core a similar substance, though not quite so hard and infusible, known as carborundum sand or siloxicon. This is mixed with fire clay and used for furnace linings. Many new forms of refractories have come into use to meet the demands of the new high temperature work. The essentials are that it should not melt or crumble at high heat, and should not expand and contract greatly under changes of temperature, low coefficient of thermal expansion. Whether it is desirable that it should heat through readily or slowly, coefficient of thermal conductivity, depends on whether it is wanted as a crucible or as a furnace lining. Lime, calcium oxide, fuses only at the highest heat of the electric furnace, but it breaks down into dust. Magnesia, magnesium oxide, is better and is most extensively employed. For every ton of steel produced, 5 pounds of magnesite is needed. Formerly, we imported 90% of our supply from Austria, but now we get it from California and Washington. In 1913, the American production of magnesite was only 9,600 tons. In 1918, it was 225,000. Zirconium oxide, is still more refractory, and in spite of its greater cost, zircite is coming into use as a lining for electric furnaces. Silicon is next to oxygen the commonest element in the world. It forms a quarter of the Earth's crust, yet it is unfamiliar to most of us. That is because it is always found combined with oxygen in the form of silica as quartz crystal or sand. This used to be considered too refractory to be blown, but is found to be easily manipulable at the high temperatures now at the command of the glass blower. So the chemist rejoices in flasks that he can heat red hot in the Bunsen burner and then plunge into ice water without breaking, and the cook can bake and serve in a dish of pyrex, which is 80% silica. At the beginning of the 20th century, minute specimens of silicon were sold as laboratory curiosities at the price of $100 an ounce. 2 years later it was turned out by the barrelful at Niagara as an accidental byproduct and could not find a market at 10 cents a pound. Silicon from the electric furnace appears in the form of hard, glittering metallic crystals. An alloy of iron and silicon, ferrosilicon, made by heating a mixture of iron ore, sand, and coke in the electrical furnace, is used as a deoxidizing agent in the manufacture of steel. Since silicon has been robbed with difficulty of its oxygen, it takes it on again with great avidity. This has been made use of in the making of hydrogen. A mixture of silicon, or of the ferrosilicon alloy containing 90% of silicon, with soda and slaked lime, is inert, compact, and can be transported to any point where hydrogen is needed, say at a battlefront. Then the hydrogenite, as the mixture is named, is ignited by a hot iron ball and goes off like thermite, with the production of great heat and the evolution of a vast volume of hydrogen gas. Or the ferrosilicon may be simply burned in an atmosphere of steam in a closed tank after ignition with a pinch of gunpowder. The iron and the silicon revert to their oxides while the hydrogen of the water is set free. The French silicol method consists in treating silicon with a 40% solution of soda. Another source of hydrogen, originating with the electric furnace, is hydrolith, which consists of calcium hydride. Metallic calcium is prepared from lime in the electric furnace. Then, pieces of the calcium are spread out in an oven heated by electricity, and a current of dry hydrogen passed through. The gas is absorbed by the metal, forming the hydride, CaH2. This is packed up in cans, and when hydrogen is desired, it is simply dropped into water, when it gives off the gas just as calcium carbide gives off acetylene. This last reaction was also used in Germany for filling zeppelins, for calcium carbide is convenient and portable, and acetylene, when it is once started, as by an electric shock, decomposes spontaneously by its own internal heat into hydrogen and carbon. The latter is left as a fine, pure lampblack, suitable for printer's ink. Napoleon, who was always on the lookout for new inventions that could be utilized for military purposes, seized immediately upon the balloon as an observation station. Within a few years after the first ascent had been made in Paris, Napoleon took balloons and apparatus for generating hydrogen with him on his archaeological expedition to Egypt, in which he hoped to conquer Asia. But the British fleet in the Mediterranean put a stop to this experiment by intercepting the ship, and military aviation waited until the Great War for its full development. This caused a sudden demand for immense quantities of hydrogen, and all manner of means was taken to get it. Water is easily decomposed into hydrogen and oxygen by passing an electric current through it. In various electrolytical processes, hydrogen has been a wasted byproduct since the balloon demand was slight, and it was more bother than it was worth to collect and purify the hydrogen. Another way of getting hydrogen in quantity is by passing steam over red-hot coke. This produces the blue water gas, which contains about 50% hydrogen, 40% carbon monoxide, and the rest nitrogen and carbon dioxide. The last is removed by running the mixed gases through lime. Then the nitrogen and carbon monoxide are frozen out in an air liquefying apparatus, and the hydrogen escapes to the storage tank. The liquefied carbon monoxide, allowed to regain its gaseous form, is used in an internal combustion engine to run the plant. There are then many ways of producing hydrogen, but it is so light and bulky that it is difficult to get it where it is wanted. The American government in the war made use of steel cylinders, each holding 161 cubic feet of the gas under a pressure of 2,000 pounds per square inch. Even the hydrogen used by the troops in France was shipped from America in this form. For field use, the ferrosilicon and soda process was adopted. A portable generator of this type was capable of producing 10,000 cubic feet of the gas per hour. The discovery by a Kansas chemist of natural sources of helium may make it possible to free ballooning of its great danger, for helium is non-inflammable and almost as light as hydrogen. Other uses of hydrogen besides ballooning have already been referred to in other chapters. It is combined with nitrogen to form synthetic ammonia. It is combined with oxygen in the oxyhydrogen blowpipe to produce heat. It is combined with vegetable and animal oils to convert them into solid fats. There is also the possibility of using it as a fuel in the internal combustion engine in place of gasoline, but for this purpose we must find some way of getting hydrogen portable or producible in a compact form. Aluminum, like silicon, sodium and calcium, has been rescued by violence from its attachment to oxygen, and like these metals it reverts with readiness to its former affinity. Dr. Goldschmidt made use of this reaction in his thermite process. Powdered aluminum is mixed with iron oxide, rust. If the mixture is heated at any point, a furious struggle takes place throughout the whole mass between the iron and the aluminum as to which metal shall get the oxygen, and the aluminum always comes out ahead. The temperature runs up to some 6,000 degrees Fahrenheit within 30 seconds, and the freed iron, completely liquefied, runs down into the bottom of the crucible, where it may be drawn off by opening a trap door. The newly formed aluminum oxide, alumina, floats as slag on top. The applications of the thermite process are innumerable. If, for instance, it is desired to mend a broken rail or crankshaft without moving it from its place, the two ends are brought together or fixed at the proper distance apart. A crucible filled with the thermite mixture is set up above the joint and the thermite ignited with a priming of aluminum and barium peroxide to start it off. The barium peroxide, having a superabundance of oxygen, gives it up readily, and the aluminum thus encouraged attacks the iron oxide and robs it of its oxygen. As soon as the iron is melted, it is run off through the bottom of the crucible and fills the space between the rail ends, being kept from spreading by a mold of refractory material such as magnesite. The two ends of the rail are therefore joined by a section of the same size, shape, substance and strength as themselves. The same process can be used for mending a fracture or supplying a missing fragment of a steel casting of any size, such as a ship's propeller or a cogwheel. For smaller work, thermite has two rivals, the oxyacetylene torch and electric welding. The former has been described and the latter is rather out of the range of this volume, although I may mention that in the latter part of 1918 there was launched from a British shipyard the first rivetless steel vessel. In this, the steel plates forming the shell, bulkheads, and floors are welded instead of being fastened together by rivets. There are three methods of doing this depending upon the thickness of the plates and the sort of strain they are subject to. The plates may be overlapped and tacked together at intervals by pressing the two electrodes on opposite sides of the same point until the spot is sufficiently heated to fuse together the plates here. Or roller electrodes may be drawn slowly along the line of the desired weld, fusing the plates together continuously as they go. Or, thirdly, the plates may be butt welded by being pushed together edge to edge without overlapping, and the electric current being passed from one plate to the other heats up the joint where the conductivity is interrupted. It will be observed that the thermite process is essentially like the ordinary blast furnace process of smelting iron and other metals except that aluminum is used instead of carbon to take the oxygen away from the metal in the ore. This has an advantage in case carbon-free metals are desired and the process is used for producing manganese, tungsten, titanium, molybdenum, vanadium and their alloys with iron and copper. During the war, thermite found a new and terrible employment, as it was used by the airmen for setting buildings on fire and exploding ammunition dumps. The German incendiary bombs consisted of a perforated steel nosepiece, a tail to keep it falling straight, and a cylindrical body which contained a tube of thermite packed around with mineral wax containing potassium perchlorate. The fuse was ignited as the missile was released, and the thermite, as it heated up, melted the wax and allowed it to flow out together with the liquid iron through the holes in the nosepiece. The American incendiary bombs were of a still more malignant type. They weighed about 40 pounds apiece and were charged with oil emulsion, thermite and metallic sodium. Sodium decomposes water so that if any attempt were made to put it out with a hose, a fire started by one of these bombs, the stream of water would be instantaneously changed into a jet of blazing hydrogen. Besides its use in combining and separating different elements, the electric furnace is able to change a single element into its various forms. Carbon, for instance, is found in three very distinct forms: in hard, transparent, and colorless crystals as the diamond, in black, opaque, metallic scales as graphite, and in shapeless masses and powder as charcoal, coke, lampblack, and the like. In the intense heat of the electric arc these forms are convertible one into the other according to the conditions. Since the third form is the cheapest, the object is to change it into one of the other two. Graphite, plumbago, or black lead, as it is still sometimes called, is not found in many places and more rarely found pure. The supply was not equal to the demand until Acheson worked out the process of making it by packing powdered anthracite between the electrodes of his furnace. In this way graphite can be cheaply produced in any desired quantity and quality. Since graphite is infusible and incombustible except at exceedingly high temperatures, it is extensively used for crucibles and electrodes. These electrodes are made in all sizes for the various forms of electric lamps and furnaces from rods 1/16 of an inch in diameter to bars a foot thick and 6 feet long. It is graphite mixed with fine clay to give it the desired degree of hardness that forms the filling of our lead pencils. Finely ground and flocculent graphite treated with tannin may be held in suspension in liquids and even pass through filter paper. The mixture with water is sold under the name of aquadag, with oil as oildag, and with grease as gredag for lubrication. The smooth, slippery scales of graphite in suspension slide over each other easily and keep the bearings from rubbing against each other. The other and more difficult metamorphosis of carbon, the transformation of charcoal into diamond, was successfully accomplished by Moissan in 1894. Henri Moissan was a toxicologist, that is to say, a professor of poisoning in the Paris School of Pharmacy, who took to experimenting with the electric furnace in his leisure hours and did more to demonstrate its possibilities than any other man. With it he isolated fluorine, most active of the elements, and he prepared for the first time in their purity many of the rare metals that have since found industrial employment. He also made the carbides of the various metals, including the now common calcium carbide. Among the problems that he undertook and solved was the manufacture of artificial diamonds. He first made pure charcoal by burning sugar. This was packed with iron in the hollow of a block of lime into which was extended from opposite sides the carbon rods connected to the dynamo. When the iron had melted and dissolved all the carbon it could, Moissan dumped into it water or better into melted lead or into a hole in a copper block, for this cooled it most rapidly. After a crust was formed it was left to solidify slowly. The sudden cooling of the iron on the outside subjected the carbon, which was held in solution, to intense pressure, and when the bit of iron was dissolved in acid, some of the carbon was found to be crystallized as diamond, although most of it was graphite. To be sure, the diamonds were hardly big enough to be seen with the naked eye, but since Moissan's aim was to make diamonds, not big diamonds, he ceased his efforts at this point. To produce large diamonds the carbon would have to be liquefied in considerable quantity and kept in that state while it slowly crystallized, but that could only be accomplished at a temperature and pressure and duration unattainable as yet. Under ordinary atmospheric pressure carbon passes over from the solid to the gaseous phase without passing through the liquid, just as snow on a cold, clear day will evaporate without melting. Probably someone in the future will take up the problem where Moissan dropped it and find out how to make diamonds of any size. But it is not a question that greatly interests either the scientist or the industrialist, because there is not much to be learned from it, and not much to be made out of it. If the inventor of a process for making cheap diamonds could keep his electric furnace secretly in his cellar and market his diamonds cautiously, he might get rich out of it, but he would not dare to turn out very large stones, or too many of them, for if a suspicion got around that he was making them, the price would fall to almost nothing, even if he did sell another one. For the high price of the diamond is purely fictitious. It is in the first place kept up by limiting the output of the natural stone by the combination of dealers, and, further, the diamond is valued not for its usefulness or beauty, but by its real or supposed rarity. Chesterton says, "All is gold that glitters, for the glitter is the gold." This is not so true of gold, for if gold were as cheap as nickel it would be very valuable, since we should gold plate our machinery, our ships, our bridges, and our roofs. But if diamonds were cheap, they would be good for nothing except grindstones and drills. An imitation diamond made of heavy glass, paste, cannot be distinguished from the genuine gem except by an expert. It sparkles about as brilliantly, for its refractive index is nearly as high. The reason why it is not priced so highly is because the natural stone has presumably been obtained through the toil and sweat of hundreds of Negroes searching in the blue ground of the Transvaal for many months. It is valued exclusively by its cost. To wear a diamond necklace is the same as hanging a certified check for $100,000 by a string around the neck. Real values are enhanced by reduction in the cost of the price of production. Fictitious values are destroyed by it. Aluminum at 25 cents a pound is immensely more valuable to the world than when it is a curiosity in the chemist's cabinet and priced at $160 a pound. So the scope of the electric furnace reaches from the costly but comparatively valueless diamond to the cheap but indispensable steel. As F. J. Tone says, if the automobile manufacturers were deprived of Niagara products, the abrasives, aluminum, acetylene for welding, and high-speed tool steel, a factory now turning out 500 cars a day would be reduced to 100. I have here been chiefly concerned with electricity as effecting chemical changes in combining or separating elements, but I must not omit to mention its rapidly extending use as a source of heat, as in the production and casting of steel. In 1908 there were only 55 tons of steel produced by the electric furnace in the United States, but by 1918 this had risen to 511,364 tons. And besides ordinary steel, the electric furnace has given us alloys of iron with the once rare metals that have created a new science of metallurgy. End of chapter 13. End of section 14. Section 15. Chapter 14, Part 1 of 2. Of Creative Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, 2010. Creative Chemistry by Edwin E. Slosson. Chapter 14, Part 1 of 2. Metals Old and New. The primitive metallurgist could only make use of such metals as he found free in nature, that is, such as had not been attacked and corroded by the ubiquitous oxygen. These were primarily gold or copper, though possibly some original genius may have happened upon a bit of meteoric iron and pounded it out into a sword. But when man had found that the red ochre he had hitherto used only as a cosmetic could be made to yield iron by melting it with charcoal, he opened a new era in civilization, though doubtless the ochre artists of that day denounced him as a utilitarian and deplored the decadence of the times. Iron is one of the most timid of metals. It has a great disinclination to be alone. It is also one of the most altruistic of the elements. It likes almost every other element better than itself. It has an especial affection for oxygen, and since this is in both air and water, and these are everywhere, iron is not long without a mate. The result of this union goes by various names in the mineralogical and chemical worlds, but in common language, which is quite good enough for our purpose, it is called iron rust. Not many of us have ever seen iron, the pure metal, soft, ductile, and white like silver. As soon as it is exposed to the air, it veils itself with a thin film of rust, and becomes black and then red. For that reason there is practically no iron in the world, except what man has made. It is rarer than gold, than diamonds. We find in the earth no nuggets or crystals of it the size of the fist as we find of these. But occasionally there fall down upon us out of the clear sky great chunks of it weighing tons. These meteorites are the mavericks of the universe. We do not know where they come from or what sun or planet they belong to. They are our only visitors from space, and if all the other spheres are like these fragments, we know we are alone in the universe, for they contain rustless iron, and where iron does not rust man cannot live, nor can any other animal or any plant. Iron rusts for the same reason that a stone rolls downhill, because it gets rid of its energy that way. All things in the universe are constantly trying to get rid of energy except man, who is always trying to get more of it. Or, on second thought, we see that man is the greatest spendthrift of all, for he wants to expend so much more energy than he has that he borrows from the winds, the streams, and the coal in the rocks. He robs minerals and plants of the energy which they have stored up to spend for their own purposes, just as he robs the bee of its honey and the silkworm of its cocoon. Man's chief business is in reversing the processes of nature. That is the way he gets his living. And one of his greatest triumphs was when he discovered how to undo iron rust and get the metal out of it. In the 4,000 years since he first did this, he has accomplished more than in the millions of years before. Without knowing the value of iron rust, man could attain only to the culture of the Aztecs and Incas, the ancient Egyptians and Assyrians. The prosperity of modern states is dependent on the amount of iron rust which they possess and utilize. England, United States, Germany, all nations are competing to see which can dig up the most iron rust out of the ground and make out of it railroads, bridges, buildings, machinery, battleships and such other tools and toys, and then let them relapse into rust again. Civilization can be measured by the amount of iron rusted per capita, or better, by the amount rescued from rust. But we are devoting so much space to the consideration of the material aspects of iron that we are like to neglect its aesthetic and ethical uses. The beauty of nature is very largely dependent upon the fact that iron rust and, in fact, all the common compounds of iron are colored. Few elements can assume so many tints. Look at the paint pot canyons of the Yellowstone. Cheap glass bottles turn out brown, green, blue, yellow or black, according to the amount and kind of iron they contain. We build a house of cream-colored brick, varied with speckled brick and adorned with terracotta ornaments of red, yellow and green, all due to iron. Iron rusts, therefore it must be painted. But what is there better to paint it with than iron rust itself? It is cheap and durable, for it cannot rust any more than a dead man can die. And what is also of importance, it is a good, strong, clean looking, endurable color. Whenever we take a trip on the railroad and see the miles of cars, the acres of roofing and wall, the towns full of brick buildings, we rejoice that iron rust is red, not white or some less satisfying color. We do not know why it is so. Zinc and aluminum are metals very much like iron in chemical properties, but all their salts are colorless. Why is it that the most useful of the metals forms the most beautiful compounds? Some say providence, some say chance, some say nothing. But if it had not been so, we would have lost most of the beauty of rocks and trees and human beings, for the leaves and the flowers would all be white, and all the men and women would look like walking corpses. Without color in the flower, what would the bees and painters do? If all the grass and trees were white, It would be like winter all the year round. If we had white blood in our veins like some of the insects, it would be hard lines for our poets. And what would become of our morality if we could not blush? As for me, I thrill to see The bloom a velvet cheek discloses. Made of dust, I well believe it. So are lilies, so are roses. An etiolated earth would hardly be worth living in. The chlorophyll of the leaves and the hemoglobin of the blood are similar in constitution. Chlorophyll contains magnesium in place of iron, but iron is necessary to its formation. We all know how pale a plant gets if its soil is short of iron. It is the iron in the leaves that enables the plants to store up the energy of the sunshine for their own use and ours. It is the iron in our blood that enables us to get the iron out of iron rust and make it into machines to supplement our feeble hands. Iron is for us internally the carrier of energy, just as in the form of a trolley wire or of a third rail it conveys power to the electric car. Withdraw the iron from the blood, as indicated by the pallor of the cheeks, and we become weak, faint, and finally die. If the amount of iron in the blood gets too small, the disease germs that are always attacking us are no longer destroyed, but multiply without check and conquer us. When the iron ceases to work efficiently, we are killed by the poison we ourselves generate. Counting the number of iron-bearing corpuscles in the blood is now a common method of determining disease. It might also be useful in moral diagnosis. A microscopical and chemical laboratory attached to the courtroom would give information of more value than some of the evidence now obtained. For the anemic and the florid vices need very different treatment. An excess or a deficiency of iron in the body is liable to result in criminality. A chemical system of morals might be developed on this basis. Among the ferruginous sins would be placed murder, violence, and licentiousness. Among the non-ferruginous, cowardice, sloth, and lying. The former would be mostly sins of commission, the latter sins of omission. The virtues could, of course, be similarly classified. The ferruginous virtues would include courage, self-reliance, and hopefulness; the non-ferruginous, peaceableness, meekness, and chastity. According to this ethical criterion, the moral man would be defined as one whose conduct is better than we should expect from the percent of iron in his blood. The reason why iron is able to serve this unique purpose of conveying life-giving air to all parts of the body is because it rusts so readily. Oxidation and deoxidation proceed so quietly that the tenderest cells are fed without injury. The blood changes from red to blue, and vice versa, with greater ease and rapidity than in the corresponding alterations of social status in a democracy. It is because iron is so rustable that it is so useful. The factories with big scrap heaps of rusting machinery are making the most money. The pyramids are the most enduring structures raised by the hand of man, but they have not sheltered so many people in their 40 centuries as our skyscrapers that are already rusting. We have to carry on this eternal conflict against rust because oxygen is the most ubiquitous of the elements and iron can only escape its ardent embraces by hiding away in the center of the earth. The united elements, known to the chemist as iron oxide and to the outside world as rust, are among the commonest compounds, and their colors, yellow and red like the Spanish flag, are displayed on every mountainside. From the time of Tubal Cain man has ceaselessly labored to divorce these elements and, having once separated them, to keep them apart so that the iron may be retained in his service. But here, as usual, man is fighting against nature and his gains, as always, are only temporary. Sooner or later his vigilance is circumvented, and the metal that he has extricated by the fiery furnace returns to its natural affinity. The flint arrowheads, the bronze spear points, the gold ornaments, the wooden idols of prehistoric man are still to be seen in our museums, but his earliest steel swords have long since crumbled into dust. Every year the blast furnaces of the world release 72,000,000 tons of iron from its oxides, and every year a large part, said to be a quarter of that amount, reverts to its primeval forms. If so, then man after 5,000 years of metallurgical industry has barely got 3 years ahead of nature, and should he cease his efforts for a generation, there would be little left to show that man had ever learned to extract iron from its ores. The old question, "What becomes of all the pins?" may be as well asked of rails, pipes, and threshing machines. The end of all iron is the same. However many may be its metamorphoses while in the service of man, it relapses at last into its original state of oxidation. To save a pound of iron from corrosion is then as much a benefit to the world as to produce another pound from the ore. In fact, it is of much greater benefit, for it takes 4 pounds of coal to produce 1 pound of steel. So whenever a piece of iron is allowed to oxidize, it means that 4 times as much coal must be oxidized in order to replace it. And the beds of coal will be exhausted before the beds of iron ore. If we are ever to get ahead, if we are to gain any respite from this enormous waste of labor and natural resources, we must find ways of preventing the iron which we have obtained and fashioned into useful tools from being lost through oxidation. Now there is only one way of keeping iron and oxygen from uniting, and that is to keep them apart. A very thin dividing wall will serve for the purpose, for instance, a film of oil. But ordinary oil will rub off, so it is better to cover the surface with an oil-like linseed which oxidizes to a hard elastic and adhesive coating. If with linseed oil we mix iron oxide or some other pigment, we have a paint that will protect iron perfectly so long as it is unbroken. But let the paint wear off or crack so that air can get at the iron, then rust will form and spread underneath the paint on all sides. The same is true of the porcelain-like enamel with which our kitchen iron ware is nowadays coated. So long as the enamel holds it is all right, but once it is broken through at any point it begins to scale off and gets into our food. Obviously, it would be better for some purposes if we could coat our iron with another and less easily oxidized metal than with such dissimilar substances as paint or porcelain. Now the nearest relative to iron is nickel, and a layer of this of any desired thickness may be easily deposited by electricity upon any surface however irregular. Nickel takes a bright polish and keeps it well, so nickel plating has become the favorite method of protection for small objects where the expense is not prohibitive. Copper plating is used for fine wires. A sheet of iron dipped in melted tin comes out coated with a thin adhesive layer of the latter metal. Such tinned plate, commonly known as tin, has become the favorite material for pans and cans. But if the tin is scratched, the iron beneath rusts more rapidly than if the tin were not there, for an electrolytic action is set up and the iron, being the negative element of the couple, suffers at the expense of the tin. With zinc it is quite the opposite. Zinc is negative toward iron, so when the two are in contact and exposed to the weather the zinc is oxidized first. A zinc plating affords the protection of a Swiss guard. It holds out as long as possible, and when broken it perishes to the last atom before it lets the oxygen get at the iron. The zinc may be applied in four different ways. 1. It may be deposited by electrolysis as in nickel plating, but the zinc coating is more apt to be porous. 2. The sheets or articles may be dipped in a bath of melted zinc. This gives us the familiar galvanized iron, the most useful and when well done the most effective of rust preventives. Besides these older methods of applying zinc, there are now two new ones. 3. One is the Shoop process, by which a wire of zinc or other metal is fed into an oxyhydrogen air blast of such heat and power that is projected as a spray of minute drops with the speed of bullets, and any object subjected to the bombardment of this metallic mist receives a coating as thick as desired. The zinc spray is so fine and cool that it may be received on cloth, lace, or the bare hand. The Shoop metallizing process has recently been improved by the use of the electric current instead of the blowpipe for melting the metal. Two zinc wires connected with any electric system, preferably the direct, are fed into the pistil. Where the wires meet, an electric arc is set up and the melted zinc is sprayed out by a jet of compressed air. 4. In the Sherardizing process, the articles are put into a tight drum with zinc dust and heated to 800 degrees Fahrenheit. The zinc at this temperature attacks the iron and forms a series of alloys ranging from pure zinc on the top to pure iron on the bottom of the coating. Even if this cracks in part, the iron is more or less protected from corrosion so long as any zinc remains. Aluminum is used similarly in the calorizing process for coating iron, copper, or brass. First, a surface alloy is formed by heating the metal with aluminum powder. Then the temperature is raised to a high degree so as to cause the aluminum on the surface to diffuse into the metal and afterwards it is again baked in contact with aluminum dust, which puts upon it a protective plating of the pure aluminum which does not oxidize. Another way of protecting ironware from rusting is to rust it. This is a sort of prophylactic method like that adopted by modern medicine, where inoculation with a mild culture prevents a serious attack of the disease. The action of air and water on iron forms a series of compounds and mixtures of them. Those that contain least oxygen are hard, black, and magnetic like iron itself. Those that have most oxygen are red and yellow powders. By putting on a tight coating of the black oxide we can prevent or hinder the oxidation from going on into the pulverulent stage. This is done in several ways. In the Bauer-Barff process, the articles to be treated are put into a closed retort and a current of superheated steam passed through for 20 minutes, followed by a current of producer gas, carbon monoxide, to reduce any higher oxides that may have been formed. In the Gessner process, a current of gasoline vapor is used as the reducing agent. The bluing of watch hands, buckles, and the like may be done by dipping them into an oxidizing bath such as melted saltpeter. But in order to afford complete protection, the layer of black oxide must be thickened by repeating the process, which adds to the time and expense. This causes a slight enlargement, and the high temperature often warps the ware, so it is not suitable for nicely adjusted parts of machinery, and of course tools would lose their temper by the heat. A new method of rust proofing which is free from these disadvantages is the phosphate process, invented by Thomas Watts Coslett, an English chemist, in 1907, developed in America by the Parker Company of Detroit. This consists simply in dipping the sheet iron or articles into a tank filled with a dilute solution of iron phosphate, heated nearly to the boiling point by steam pipes. Bubbles of hydrogen stream off rapidly at first, then slower, and at the end of half an hour or longer the action ceases and the process is complete. What has happened is that the iron has been converted into a basic iron phosphate to a depth depending upon the density of articles processed. Any one who has studied elementary qualitative analysis will remember that when he added ammonia to his unknown solution, iron and phosphoric acid, if present, were precipitated together, or in other words, iron phosphate is insoluble except in acids. Therefore a superficial film of such phosphate will protect the iron underneath except from acids. The film is not a coating added on the outside like paint and enamel or tin and nickel plate. It is therefore not apt to scale off and does not increase the size of the article. No high heat is required as in the Sherardizing and Bauer-Barff process, so steel tools can be treated without losing their temper or edge. The deposit consisting of ferrous and ferric phosphates mixed with black iron oxide may be varied in composition, texture, and color. It is ordinarily a dull gray and oiling gives a soft matte black, more in accordance with modern taste than the shiny nickel plating that delighted our fathers. Even the military nowadays show more quiet taste than formerly and have abandoned their glittering accoutrements. The phosphate bath is not expensive and can be used continuously for months by adding more of the concentrated solution to keep up the strength and removing the sludge that is precipitated. Besides the iron, the solution contains the phosphates of other metals such as calcium or strontium, manganese, molybdenum, or tungsten, according to the particular purpose. Since the phosphating solution does not act on nickel, it may be used on articles that have been partly nickel plated, so there may be produced, for instance, a bright raised design against a dull black background. Then, too, the surface left by the Parker process is finely etched, so it affords a good attachment for paint or enamel if further protection is needed. Even if the enamel does crack, the iron beneath is not so apt to rust and scale off the coating. These, then, are some of the methods which are now being used to combat our eternal enemy, the rust that doth corrupt. All of them are useful in their several ways. No one of them is best for all purposes. The claim of rust proof is no more to be taken seriously than fire proof. We should rather, if we were finical, to have to speak of rust resisting coatings, as we do of slow burning buildings. Nature is insidious and unceasing in her efforts to bring to ruin the achievements of mankind, and we need all the weapons we can find to frustrate her destructive determination. But it is not enough for us to make iron superficially resistant to rust from the atmosphere. We should like also to make it so that it would withstand corrosion by acids. Then it could be used in place of the large and expensive platinum or porcelain evaporating pans and similar utensils employed in chemical works. This requirement also has been met in the non-corrosive forms of iron, which have come into use within the last 5 years. One of these, tant iron, developed by a British metallurgist, Robert N. Lennox, in 1912, contains 12% of silicon. Similar products are known as dur iron and buffolast in America, metallure in France, ileonite in Italy, and neutralizin in Germany. It is a silvery white, close-grained iron, very hard and rather brittle, somewhat like cast iron but with silicon as the main additional ingredient in place of carbon. It is difficult to cut or drill, but may be ground into shape by the new abrasives. It is rust-proof and is not attacked by sulfuric, nitric, or acetic acid, hot or cold, diluted or concentrated. It does not resist so well hydrochloric acid or sulfur dioxide or alkalis. The value of iron lies in its versatility. It is a dozen metals in one. It can be made hard or soft, brittle or malleable, tough or weak, resistant or flexible, elastic or pliant, magnetic or non-magnetic, more or less conductive to electricity by slight changes of composition or mere differences of treatment. No wonder that the medieval mind ascribed these mysterious transformations to witchcraft. But the modern micrometallurgist, by etching the surface of steel and photographing it, shows it up as composite as a block of granite. He is then able to pick out its component minerals, ferrite, austenite, martensite, pearlite, graphite, cementite, and to show how their abundance, shape, and arrangement contribute to the strength or weakness of the specimen. The last of these constituents, cementite, is a definite chemical compound, an iron carbide, Fe3C, containing 6.6% of carbon, so hard as to scratch glass, very brittle, and imparting these properties to hardened steel and cast iron. With this knowledge at his disposal, the iron maker can work with his eyes open and so regulate his melt as to cause these various constituents to crystallize out as he wants them to. Besides, he is no longer confined to the alloys of iron and carbon. He has ransacked the chemical dictionary to find new elements to add to his alloys, and some of these rarities have proved to possess great practical value. Vanadium, for instance, used to be put into a fine print paragraph in the back of the chemistry book, where the class did not get to it until the term closed. Yet if it had not been for vanadium steel we should have no Ford cars. Tungsten, too, was relegated to the rear, and if the student remembered it at all it was because it bothered him to understand why its symbol should be W instead of T. But the student of today studies his lesson in the light of a tungsten wire and relieves his mind by listening to a phonograph record played with a tungstone stylus. When I was assistant in chemistry an analysis of steel consisted merely in the determination of its percentage of carbon, and I used to take Saturday for it so I could have time enough to complete the combustion. Now the chemists of a steel works laboratory may have to determine also the tungsten, chromium, vanadium, titanium, nickel, cobalt, phosphorus, molybdenum, manganese, silicon, and sulfur, any or all of them, and to be spry about it, because if they do not get the report out within 15 minutes while the steel is melting in the electrical furnace, the whole batch of 75 tons may go wrong. I'm glad I quit the laboratory before they got to speeding up chemists so. The quality of the steel depends upon the presence and the relative proportions of these ingredients, and a variation of 0.1% in certain of them will make a different metal out of it. For instance, the steel becomes stronger and tougher as the proportion of nickel is increased up to about 15%. Raising the percentage to 25, we get an alloy that does not rust or corrode and is non-magnetic, although both its component metals, iron and nickel, are by themselves attracted by the magnet. With 36% nickel and 5% manganese we get the alloy known as Invar because it expands and contracts very little with changes of temperature. A bar of the best form of Invar will expand less than 1/millionth part of its length for a rise of 1 degree centigrade at ordinary atmospheric temperature. For this reason it is used in watches and measuring instruments. The alloy of iron with 46% nickel is called palatine because its rate of expansion and contraction is the same as platinum and glass, so it can be used to replace the platinum wire passing through the glass of an electric light bulb. A manganese steel of 11 to 14% is too hard to be machined. It has to be cast or ground into shape and is used for burglar-proof safes and armor plate. Chrome steel is also hard and tough and finds use in files, ball bearings, and projectiles. Titanium, which the iron maker used to regard as his implacable enemy, has been drafted into service as a deoxidizer, increasing the strength and elasticity of the steel. It is reported from France that the addition of 0.3% of zirconium to nickel steel has made it more resistant to the German perforating bullets than any steel hitherto known. The new stainless cutlery contains 12 to 14% of chromium. End of chapter 14, part 1 of 2. End of section 15. Section 16, Chapter 14, Part 2 of 2, of Creative Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, 2010. Creative Chemistry by Edwin E. Slosson. Chapter 14, Part 2 of 2. With the introduction of harder steels came the need of tougher tools to work them. Now the virtue of a good tool steel is the same as of a good man. It must be able to get hot without losing its temper. Steel of the old-fashioned sort, as everybody knows, gets its temper by being heated to redness and suddenly cooled by quenching or plunging it into water or oil. But when the point gets heated up again, as it does by friction in a lathe, it softens and loses its cutting edge. So the necessity of keeping the tool cool limited the speed of the machine. But about 1868 a Sheffield metallurgist, Robert F. Mushet, found that a piece of steel he was working with did not require quenching to harden it. He had it analyzed to discover the meaning of this peculiarity and learned that it contained tungsten, a rare metal unrecognized in the metallurgy of that day. Further investigation showed that steel to which tungsten and manganese or chromium had been added was tougher and retained its temper at high temperature better than ordinary carbon steel. Tools made from it could be worked up to a white heat without losing their cutting power. The new tools of this type, invented by Efficiency Taylor at the Bethlehem Steel Works in the 90s, have revolutionized shop practice the world over. A tool of the old sort could not cut at a rate faster than 30 feet a minute without overheating, but the new tungsten tools will plow through steel 10 times as fast and can cut away a ton of the material in an hour. By means of these high-speed tools, the United States was able to turn out 5 times the munitions that it could otherwise have done in the same time. On the other hand, if Germany alone had possessed the secret of the modern steels, no power could have withstood her. A slight superiority in metallurgy has been the deciding factor in many a battle. Those of my readers who have had the advantages of Sunday school training will recall the case described in 1 Samuel chapter 13 verses 19 through 22. By means of these new materials, armor plate has been made invulnerable, except to projectiles pointed with similar material. Flying has been made possible through engines weighing no more than 2 pounds per horsepower. The cylinders of combustion engines and the casing of cannon have been made to withstand the unprecedented pressure and corrosive action of the fiery gases evolved within. Castings are made so hard that they cannot be cut, save with tools of the same sort. In the high-speed tools now used, 20 or 30% of the iron is displaced by other ingredients. For example, tungsten from 14 to 25%, chromium from 2 to 7%, vanadium from 1/2 to 1.5%, carbon from 6 to 8%, with perhaps cobalt up to 4%. Molybdenum or uranium may replace part of the tungsten. Some of the newer alloys for high-speed tools contain no iron at all. That which bears the poetic name of starstone, stellite, is composed of chromium, cobalt, and tungsten in varying proportions. Stellite keeps a hard cutting edge and gets tougher as it gets hotter. It is very hard and good for jewelry as platinum, except that it is not so expensive. Cooperite, its rival, is an alloy of nickel and zirconium, stronger, lighter, and cheaper than stellite. Before the war nearly half of the world's supply of tungsten ore, wolframite, came from Burma, but although Burma had belonged to the British for 100 years, they had not developed its mineral resources, and the tungsten trade was monopolized by the Germans. All the iron ore was shipped to Germany, and the British Admiralty was content to buy from the Germans what tungsten was needed for armor plate and heavy guns. When the war broke out, the British had the ore supply, but were unable at first to work it because they were not familiar with the processes. Germany, being short of tungsten, had to sneak over a little from Baltimore in the submarine Deutschland. In the United States before the war tungsten ore was selling at $6.50 a unit, but by the beginning of 1916 it had jumped to $85 a unit. A unit is 1% of tungsten trioxide to the ton, that is, 20 pounds. Boulder County, Colorado, and San Bernardino, California, then had mining booms, reminding one of older times. Between May and December, 1918, there was manufactured in the United States more than 45.5 million pounds of tungsten steel, containing some 8 million pounds of tungsten. If tungsten ores were more abundant and the metal more easily manipulated, it would displace steel for many purposes. It is harder than steel or even quartz. It never rusts and is insoluble in acids. Its expansion by heat is one-third that of iron. It is more than twice as heavy as iron and its melting point is twice as high. Its electrical resistance is half that of iron and its tensile strength is a third greater than the strongest steel. It can be worked into wire 0.0002 of an inch in diameter, almost too thin to be seen, but as strong as copper wire 10 times the size. The tungsten wires in the electric lamps are about 0.03 of an inch in diameter, and they give 3 times the light for the same consumption of electricity as the old carbon filament. The American manufacturers of the tungsten bulb have very appropriately named their lamp Mazda after the light god of the Zoroastrians. To get the tungsten into wire form was a problem that long baffled the inventors of the world, for it was too refractory to be melted in mass and too brittle to be drawn. Dr. W. D. Coolidge succeeded in accomplishing the feat in 1912 by reducing the tungstic acid by hydrogen and molding the metallic powder into a bar by pressure. This is raised to a white heat in the electric furnace, taken out and rolled down, and the process repeated some 50 times, until the wire is small enough so it can be drawn at a red heat through diamond dies of successively smaller apertures. The German method of making the lamp filaments is to squirt a mixture of tungsten powder and thorium oxide through a perforated diamond of the desired diameter. The filament so produced is drawn through a chamber heated to 2500 degrees Celsius at a velocity of 8 feet an hour, which crystallizes the tungsten into a continuous thread. The first metallic filament used in the electric light on a commercial scale was made of tantalum, the metal of Tantalus. In the period 1905 to 1911, over 100 million Tantalus lamps were sold, but tungsten displaced them as soon as that metal could be drawn into wire. A recent rival of tungsten, both as a filament for lamps and hardener for steel, is molybdenum. 1 pound of this metal will impart more resiliency to steel than 3 or 4 pounds of tungsten. The molybdenum steel, because it does not easily crack, is said to be serviceable for armor-piercing shells, gun linings, airplane struts, automobile axles, and propeller shafts. In combination with its rival as a tungsten molybdenum alloy, it is capable of taking the place of the intolerably expensive platinum, for it resists corrosion when used for spark plugs and tooth plugs. European steel men have taken to molybdenum more than Americans. The salts of this metal can be used in dyeing and photography. Calcium, magnesium, and aluminum, common enough in their compounds, have only come into use as metals since the invention of the electric furnace. Now the photographer uses magnesium powder for his flashlight when he wants to take a picture of his friends inside the house, and the aviator uses it when he wants to take a picture of his enemies on the open field. The flares prepared by our government for the war consist of a sheet iron cylinder 4 feet long and 6 inches thick, containing a stick of magnesium attached to a tightly rolled silk parachute 20 feet in diameter when expanded. The whole weighed 32 pounds. On being dropped from the plane by pressing a button, the rush of air set spinning a pinwheel at the bottom, which ignited the magnesium stick and detonated a charge of black powder sufficient to throw off the case and release the parachute. The burning flare gave off a light of 320,000 candle power, lasting for 10 minutes as the parachute slowly descended. This illuminated the ground on the darkest night sufficiently for the airman to aim his bombs or to take photographs. The addition of 5 or 10% of magnesium to aluminum gives an alloy, magnalium, that is almost as light as aluminum and almost as strong as steel. An alloy of 90% aluminum and 10% calcium is lighter and harder than aluminum and more resistant to corrosion. The latest German airplane, the Junker, was made entirely of duralumin. Even the wings were formed of corrugated sheets of this alloy instead of the usual doped cotton cloth. Duralumin is composed of about 85% of aluminum, 5% of copper, 5% of zinc, and 2% of tin. When platinum was first discovered, it was so cheap that ingots of it were gilded and sold as gold bricks to unwary purchasers. The Russian government used it as we use nickel, for making small coins. But this is an exception to the rule that the demand creates the supply. Platinum is really a rare metal, not merely an unfamiliar one. Nowhere except in the Urals is it found in quantity, and since it seems indispensable in chemical and electrical appliances, the price has continually gone up. Russia collapsed into chaos when the war work made the heaviest demand for platinum, so the governments had to put a stop to its use for jewelry and photography. The gold brick scheme would now have to be reversed, for gold is used as a cheaper metal to adulterate platinum. All the members of the platinum family, formerly ignored, were pressed into service. Palladium, rhodium, osmium, iridium, and these, alloyed with gold or silver, were employed more or less satisfactorily by the dentist, chemist, and electrician as substitutes for the platinum of which they had been deprived. one of these alloys composed of 20% palladium and 80% gold, and bearing the telescope name of Pallau (palladium aurum), makes very acceptable crucibles for the laboratory, and only costs half as much as platinum. Rhotanium is a similar alloy recently introduced. The points of our gold pens are tipped with an osmium iridium alloy. It is a pity that this family of noble metals is so restricted, for they are unsurpassed in tenacity and incorruptibility. They could be of great service to the world in war and peace. As the Bad Child says in his Book of Beasts, "I shoot the hippopotamus with bullets made of platinum, because if I use leaden ones his hide is sure to flatten 'em." Along in the latter half of the last century chemists had begun to perceive certain regularities and relationships among the various elements, so they conceived the idea that some sort of a pigeon-hole scheme might be devised in which the elements could be filed away in the order of their atomic weights, so that one could see just how a certain element, known or unknown, would behave from merely observing its position in the series. Mendeleev, a Russian chemist, devised the most ingenious of such systems called the periodic law, and gave proof that there was something in his theory by predicting the properties of three metallic elements, then unknown, but for which his arrangement showed three empty pigeon-holes. 16 years later all of these predicted elements had been discovered, one by a Frenchman, one by a German, and one by a Scandinavian, and named from patriotic impulse, gallium, germanium, and scandium. This was a triumph of scientific prescience, as striking as the mathematical proof of the existence of the planet Neptune by Leverrier before it had been found by the telescope. But although Mendeleev's law told the truth, it gradually became evident that it did not tell the whole truth and nothing but the truth, as the lawyers put it. As usually happens in the history of science, the hypothesis was found not to explain things so simply and completely as was at first assumed. The anomalies in the arrangement did not disappear on closer study, but stuck out more conspicuously. Though Mendeleev had pointed out three missing links, he had failed to make provision for a whole group of elements since discovered, the inert gases of the helium-argon group. As we now know, the scheme was built upon the false assumptions that the elements are immutable and that their atomic weights are invariable. The elements that the chemists had most difficulty in sorting out and identifying were the heavy metals found in the rare earths. There were about 20 of them, so mixed up together and so much alike as to baffle all ordinary means of separating them. For 100 years chemists worked over them and quarreled over them before they discovered that they had a commercial value. It was a problem as remote from practicality as any that could be conceived. The man in the street did not see why chemists should care whether there were two didymiums any more than why theologians should care whether there were two Isaiahs. But all of a sudden, in 1885, the chemical puzzle became a business proposition. The rare earths became household utensils, and it made a big difference with our monthly gas bills whether the ceria and the thoria in the burner mantles were absolutely pure or contained traces of some of the other elements that were so difficult to separate. This sudden change of venue from pure to applied science came about through a Viennese chemist, Dr. Karl Auer, later and in consequence known as Baron Auer von Welsbach. He was trying to sort out the rare earths by means of the spectroscopic method, which consists ordinarily in dipping a platinum wire into a solution of the unknown substance and holding it in a colorless gas flame. As it burns off, each element gives a characteristic color to the flame, which is seen as a series of lines when looked at through the spectroscope. But the flash of the flame from the platinum wire was too brief to be studied, so Dr. Auer hit upon the plan of soaking a thread in the liquid and putting this in the gas jet. The cotton, of course, burned off at once, but the earths held together and when heated gave off a brilliant white light, very much like the calcium or lime light which is produced by heating a stick of quicklime in the oxyhydrogen flame. But these rare earths do not require any such intense heat as that, for they will glow in an ordinary gas jet. So the Welsbach mantle burner came into use everywhere and rescued the coal gas business from the destruction threatened by the electric light. It was no longer necessary to enrich the gas with oil to make its flame luminous, for a cheaper fuel gas such as is used for a gas stove will give, with a mantle, a fine white light of much higher candle power than the ordinary gas jet. The mantles are knit in narrow cylinders on machines, cut off at suitable lengths, soaked in a solution of the salts of the rare earths, and dried. Artificial silk, viscose, has been found better than cotton thread for the mantles, for it is solid, not hollow, more uniform in quality and continuous instead of broken up into 1-inch fibers. There is a great deal of difference in the quality of these mantles, as everyone who has used them knows. Some that give a bright glow at first, with the gascock only half open, will soon break up or grow dull and require more gas to get any kind of light out of them. Others will last long and grow better to the last. Slight impurities in the earths or the gas will speedily spoil the light. The best results are obtained from a mixture of 99 parts thoria and 1 part ceria. It is the ceria that gives the light, yet a little more of it will lower the luminosity. The non-chemical reader is apt to be confused by the strange names and their varied terminations, but he need not be when he learns that the new metals are given names ending in such as sodium, cerium, thorium, and that their oxides, compounds with oxygen, the earths, are given the termination a, like soda, ceria, thoria. So when he sees a name ending in the let him picture to himself a metal, any metal since they mostly look alike, lead or silver, for example. And when he comes across a name ending in a, he may imagine a white powder like lime. Thorium, for instance, is, as its name implies, a metal named after the thunder god Thor, to whom we dedicate one day in each week, Thursday. Cerium gets its name from the Roman goddess of agriculture by way of the asteroid. The chief sources of the material for the Welsbach burners is monazite, glittering yellow sand composed of phosphate of cerium with some 5% of thorium. In 1916, the United States imported 2.5 million pounds of monazite from Brazil and India, most of which used to go to Germany. In 1895 we got over 1.5 million pounds from the Carolinas, but the foreign sand is richer and cheaper. The price of the salts of the rare metals fluctuates wildly. In 1895 thorium nitrate sold at $200 a pound. In 1913 it fell to $2.60 and in 1916 it rose to $8. Since the monazite contains more cerium than thorium and the mantles made from it contain more thorium than cerium, there is a superfluity of cerium. The manufacturers give away a pound of cerium salts with every purchase of 100 pounds of thorium salts. It annoyed Welsbach to see the cerium residues thrown away and accumulating around his mantle factory, so he set out to find some use for it. He reduced the mixed earths to a metallic form and found off that it gave a shower of sparks when scratched. An alloy of cerium with 30 or 35% of iron proved the best and was put on the market in the form of automatic lighters. A big business was soon built up in Austria on the basis of this obscure chemical element rescued from the dump heap. The sale of the cerite lighters in France threatened to upset the finances of the Republic, which derived a large revenue from its monopoly of matchmaking, so the French government imposed a tax upon every man who carried one. American tourists who bought these lighters in Germany used to be much annoyed at being held up on the French frontier and compelled to take out a license. During the war the cerium sparklers were much used in the trenches for lighting cigarettes, but, as those who have seen the better Olé will know, they sometimes fail to strike fire. Our metal or cerium iron alloy was used in munitions, to ignite hand grenades and to blazon the flight of trailer shells. There are many other pyrophoric, light-producing alloys, including steel, which our ancestors used with flint before matches and percussion caps were invented. There are more than 50 metals known, and not half of them have come into common use, so there is still plenty of room for the expansion of the science of metallurgy. If the reader has not forgotten his arithmetic of permutations, he can calculate how many different alloys may be formed by varying the combinations and proportions of these 50. We have seen how quickly elements formerly known only to chemists, and to some of them known only by name, have become indispensable in our daily life. Any one of those still unutilized may be found to have peculiar properties that fit it for filling a long unfelt want in modern civilization. Who, for instance, will find a use for gallium, the metal of France? It was described in 1869 by Mendeleev in advance of its advent and has been known in person since 1875, but has not yet been set to work. It is such a remarkable metal that it must be good for something. If you saw it in a museum case on a cold day you might take it to be a piece of aluminum, but if the curator let you hold it in your hand, which he won't, it would melt and run over the floor like mercury. The melting point is 87 degrees Fahrenheit. It might be used in thermometers for measuring temperatures above the boiling point of mercury, were it not for the peculiar fact that gallium wets glass so it sticks to the side of the tube instead of forming a clear convex curve on top like mercury. Then there is columbium, the American metal. It is strange that an element named after Columbia should prove so impractical. Columbium is a metal closely resembling tantalum, and tantalum found a use as electric light filaments. A columbium lamp should appeal to our patriotism. The so-called rare elements are really abundant enough considering the earth's crust as a whole, though they are so thinly scattered that they are usually overlooked and hard to extract. But whenever one of them is found valuable it is soon found available. A systematic search generally reveals it somewhere in sufficient quantity to be worked. Who, then, will be the first to discover a use for indium, germanium, terbium, thulium, lanthanum, neodymium, scandium, samarium, and others as unknown to us as tungsten was to our fathers? As evidence of the statement that it does not matter how rare an element may be, it will come into common use if it is found to be commonly useful, we may refer to radium. A good rich specimen of radium ore, pitchblende, may contain as much as 1 part in 4,000,000. Madame Curie, the brilliant Polish Parisian, had to work for years before she could prove to the world that such an element existed, and for years afterwards before she could get the metal out. Yet now we can all afford a bit of radium to light up our watch dials in the dark. The amount needed for this is infinitesimal. If it were more it would scorch our skins, for radium is an element in eruption. The atom throws off corpuscles at intervals as a Roman candle throws off blazing balls. Some of these particles, the alpha rays, are atoms of another element, helium, charged with positive electricity, and are ejected with a velocity of 18,000 miles a second. Some of them, the beta rays, are negative electrons, only about 1/7000th the size of the others, but are ejected with almost the speed of light, 186,000 miles a second. If one of the alpha projectiles strikes a slice of zinc sulfide, it makes a splash of light big enough to be seen with a microscope, so we can follow the flight of a single atom. The luminous watch dials consist of a coating of zinc sulfide under continual bombardment by the radium projectiles. Sir William Crookes invented this radium light apparatus and called it a spinarthroscope, which is Greek for spark seer. Evidently if radium is so wasteful of its substance it cannot last forever, nor could it have forever existed. The elements, then, are not necessarily eternal and immutable, as used to be supposed. They have a natural length of life. They are born and die and propagate, at least some of them do. Radium, for instance, is the offspring of ionium, which is the great-great-grandson of uranium, the heaviest of known elements. Putting this chemical genealogy into biblical language, we might say, uranium lived 5,000,000,000 years and begot uranium X1, which lived 24.6 days and begot uranium X2, which lived 69 seconds and begot uranium 2, which lived 2,000,000 years and begot ionium, which lived 200,000 years and begot radium, which lived 1850 years and begot niton, which lived 3.85 days and begot radium A, which lived 3 minutes and begot radium B, which lived 26.8 minutes and begot radium C, which lived 19.5 minutes and begot radium D, which lived 12 years and begot radium E, which lived 5 days and begot polonium, which lived 136 days and begot lead. The figures I have given are the times when half the parent substance has gone over into the next generation. It will be seen that the chemist is even more liberal in his allowance of longevity than was Moses with the patriarchs. It appears from the above that half of the radium in any given specimen will be transformed in about 2000 years. Half of what is left will disappear in the next 2000 years, half of that in the next 2000, and so on. The reader can figure out for himself when it will all be gone. He will then have the answer to the old Eleatic conundrum of when Achilles will overtake the tortoise. But we may say that after 100,000 years there would not be any radium worth mentioning, or in other words, practically all the radium now in existence is younger than the human race. The lead that is found in uranium and has presumably descended from uranium behaves like other lead, but is lighter. Its atomic weight is only 206, while ordinary lead weighs 207. It appears, then, that the same chemical element may have different atomic weights according to its ancestry, while on the other hand different chemical elements may have the same atomic weight. This would have seemed shocking heresy to the chemists of the last century, who prided themselves on the immutability of the elements and did not take into consideration their past life or heredity. The study of these radioactive elements has led to a new atomic theory. I suppose most of us in our youth used to imagine the atom as a little round hard ball, but now it is conceived as a sort of solar system with an electropositive nucleus acting as the sun and negative electrons revolving around it like the planets. The number of free positive electrons in the nucleus varies from 1 in hydrogen to 92 in uranium. This leaves room for 92 possible elements, and of these, all but 6 are more or less certainly known and definitely placed in the scheme. The atom of uranium, weighing 238 times the atom of hydrogen, is the heaviest known and therefore the ultimate limit of the elements, though it is possible that elements may be found beyond it, just as the planet Neptune was discovered outside the orbit of Uranus. Considering the position of uranium and its numerous progeny as mentioned above, it is quite appropriate that this element should bear the name of the father of all the gods. In these radioactive elements we have come upon sources of energy such as was never dreamed of in our philosophy. The most striking peculiarity of radium is that it is always a little warmer than its surroundings, no matter how warm these may be. Slowly, spontaneously, and continuously it decomposes, and we know no way of hastening or of checking it. Whether it is cooled in liquefied air or heated to its melting point, the change goes on just the same. An ounce of radium salt will give out enough heat in 1 hour to melt an ounce of ice, and in the next hour will raise this water to the boiling point, and so on again and again without cessation for years. A fire without fuel, a realization of the philosopher's lamp that the alchemists sought in vain. The total energy so emitted is millions of times greater than produced by any chemical combination such as the union of oxygen and hydrogen to form water. From the heavy white salt there is continually rising a faint fire mist like the will-o'-the-wisp over a swamp. This gas is known as the emanation or niton, the shining one. A pound of niton would give off energy at the rate of 23,000 horsepower. Fine stuff to run a steamer, one would think, but we must remember that it does not last. By the sixth day the power would have fallen off by half. Besides, no one would dare to serve as engineer, for the radiation will rot away the flesh of a living man who comes near it, causing gnawing ulcers or curing them. It will not only break down the complex and delicate molecules of organic matter, but will attack the atom itself, changing, it is believed, one element into another, again the fulfillment of a dream of the alchemists, and its rays, unseen and unfelt by us, are yet strong enough to penetrate an armor plate and photograph what is behind it. But radium is not the most mysterious of the elements, but the least so. It is giving out the secret that the other elements have kept. It suggests to us that all the other elements in proportion to their weight have concealed within them similar stores of energy. Astronomers have long dazzled our imaginations by calculating the horsepower of the world, making us feel cheap in talking about our steam engines and dynamos when a minutest fraction of the waste dynamic energy of the solar system would make us all rich as millionaires. The heavenly bodies are too big for us to utilize in this practical fashion. And now the chemists have become as exasperating as the astronomers, for they give us a glimpse of incalculable wealth in the meanest substance. For wealth is measured by the available energy of the world, and if a few ounces of anything would drive an engine or manufacture nitrogenous fertilizer from the air, all our troubles would be over. Kipling in his sketch, With the Night Mail, and Wells in his novel, The World Set Free, stretched their imaginations in trying to tell us what it would mean to have command of this power, but they are a little hazy in their descriptions of the machinery by which it is utilized. The atom is as much beyond our reach as the moon. We cannot rob its vault of the treasure. End of chapter 14, part 2 of 2. End of section 16. End of Creative Chemistry by Edwin E. Slosson.